Приветик. Меня слышно? Алло, есть тут кто?
Да, Лёш, привет.
Все хорошо?
Да,
Отлично. А, ты не мог бы, пожалуйста, на аватарку поставить логотип конференции? Могу тебе прислать, если нужно.
он есть.
Ну все, хорошо. Ам, Никаких проблем, в принципе, быть не должно. Ам, Там остальные участники потихонечку будут
Да, Лёш.
собираться. Включи тогда демонстрацию слайда, и тогда ждем 10 утра. Без 5:10 запусти тогда всех, хорошо?
М.
Окей.
Good morning.
Good morning, everyone.
Good morning to all of you.
We will start in 3 minutes.
Okay, then I can share my presentation, I guess.
I think you can just let me give some welcoming words. First
Okay.
of all, I'm very happy to see the presenters here. I hope somebody looks our translation broadcasting, and I hope our session will be visible after it ends as a recording. I'm glad to see all of you here on the second day of POA conference. We start our session number 6, Coastal Facility Stability on Permafrost. My name is Alexey Maslakov. I am the convener of this session. Our assistant is Alexander Osipov. He helps me to lead this session. We have 4 presenters today. I'd like to remind you that we will speak only in English, no any Russian language. Presentation and answering the questions take 20 minutes. So please stick to this timing. So it's about 10, we can start. Our first presenter is Artem Nesterov with the presentation, Thermal Deformations of Frozen Soils and the Design of Hydrological Structures in the Arctic Region. Artem, please, you can start sharing your screen and start your presentation, please.
Yes, thank you. Yes, do you see my screen?
Yes, we do. You can start presentation.
Yes.
You can run it.
Yeah. So good morning, everyone. One more time. Let me please introduce further work regarding the thermal deformations of frozen soils. Laboratory experiments was conducted in 2019 at the University Central Svalbard, UNIS, Norway, in frame of CITER project. There are 3 parties of involvement in these studies, as you can see on the screen. It's Peter the Great in Petersburg Polytechnic University, the University Central Svalbard, and Nik Vedeneeva, part of Rosgidro. So the development of the Arctic regions is directly related to the intensive expansion of port infrastructure. So the specific harsh climatic conditions of the Arctic affect the design processes of the structures, including the hydrotechnical facilities, which have foundations with permafrost. Currently, there is still a problem of the characteristics monitoring during operation and determination process of soil exact parameters at the stage of design of these structures. The reason also the phase transformations within the seasonal thawing and freezing processes. Initially, much attention was paid to the problems of frost heave, but the problems associated with the behavior of frozen soils under cyclic changes of negative temperature are also important due to the presence of unfrozen water content. The phase transformations influence on thermal deformations of such type of soils. Here with compressive or tensile deformations arising in the soils under the action of the air temperature changes, which can influence on the formations frost cracks passing through the active soil layer into permafrost. It may create deformation and destruction of such type of engineering structures. Also, at the same time, ice cementation processes of mineral particles in frozen soils is a primary importance for assessing of their mechanical properties estimated by the ice content and the quantitative content of unfrozen water at a given negative temperature. At the same time, the construction of hydraulic structures in the Arctic is affected by both sea waters and also the fresh type of water. Therefore, in this work, we propose a new technique for experimental studies of temperature deformations, such type of soils saturated with water with various salinity. Yes, it was implemented. To add that knowledge of the process of thermal expansion of such soils is necessary for the design of berths and soil structures in the Arctic. This paper is a continuation of the author's work on this topic of temperature transformations of frozen soils in relation to their impact on hydrotechnical structures. Here you can see the following equipment, what we used during our studies. It's a fiber break grating sensors and thermistor strings. ABG sensor is a periodical grid with 40,000 cells built by 2 laser beams inside the fiber. The grid length is 1 centimeter. Each FBG sensor reflects the light signal of a certain wavelength, depending on the grid characteristics, tensile and temperature of the fiber. The incoming light signal is generated in the optical fiber by the source LED in the spectral range of 1,000 nanometers. The wavelengths reflected by the FBG sensors and registered for analyzing by spectrometer. To register changes inside the calibration device, a constant temperature is maintained and one of the sensors. Every channel of this unit can transfer information from 16 FBG sensors embedded in the same fiber. FBG thermistor string and stress sensor have a fiber cable with the FBG temperature sensor, which protected it from mechanical deformation by thin metal tube. It's 1 millimeter in diameter. This thermistor string includes the 12 FBG sensors embedded in the same fiber with 1 centimeter distance between each other. And also thermistor string is protected from mechanical deformation by also thin metal tube. To be added, also the important one, the accuracy of the studies. The accuracy of temperature measuring and nominal resolution is correspondingly equal to 0.4 Celsius degrees and 0.08 degrees respectively. On the next slide, you can see our samples, which we made in the UNIS laboratories. We made an artificially frozen clay samples before testing with dimensions shown on the screen. Samples was saturated with fresh and salt water. Salt water had a salinity of 34 ppt in value. One cross section, 10 centimeters, that was also made in the center of each sample. The reason for that it was a subsequent investigation of the water penetration and water freezing effects on the clay deformations. ABG temperature string and strain sensors were used to measure soil temperature and cause deformations. On the next slide, you can see the basic physical properties of the clay, such as moisture content, densities, porosity, and also grain content, and other ones. The next slide, here you can see the dependencies of the mean temperature in the soil and sea ice sample versus the time. The dependence of the air temperature near the soil surface is shown in the same figure. The air temperature amplitude was about 10 Celsius degrees in the air. It's a difference with the sample's amplitudes. It means that specific temperature conductivity of the soil is smaller than sea ice conductivity. We assume that it's probably related to this larger amount of unfrozen water in the soil samples in comparison with the amount of liquid brine in sea ice. Next one, there are measured strains of the ice and clay samples. At the beginning of the deformation curve and at each subsequent temperature switching, we can see the rapid jumps of strain in soil samples. It can be explained by softening of soil skeleton due to uneven crystallization of pore moisture content, leading to the appearance of the local microstresses and micro cracks. So with a further increase in temperature, the acquired decompaction of the soil structure also was preserved. This effect was not observed in the ice samples. This figure shows us the dependence of the strains in the soil samples and sea ice on their mean temperature. The mean temperature was calculated as the mean value of 10 temperature values measured by ABG's temperature string and different at the different depth in the soil. The hysteresis loops are well visible in the samples of saline soils and sea ice, and it's very thin in the fresh soil sample. So the mean slope of strain temperature curves shown here equals to the mean value of the linear coefficient of the thermal expansion. Herewith, studies of these coefficients of frozen soils shows that the deformability of the tested frozen soils doesn't directly depend on their mineral composition, it means salinity, but through values of the moisture content, porosity, and structural features. Here you can see temporal evolution of the strain by a red line, and temperature inside the saline soil sample after seawater was added in the cross section. So the added water was at the freezing point, and the air temperature near the soil surface, marked by gray line here, and water ice temperature inside the cross section, green line, are also shown on this figure. The air temperature near the soil surface was around -9 Celsius degrees. So significant part of the seawater was frozen inside the cut, and it's probably during the several minutes. It was, after that, only liquid brine, this high salinity left inside the soil. The moment then seawater was added in the cross section coincides with the sharp increase of the temperature inside the cut. The temperature stabilization inside the hole occurred in 1.5 hours. The soil temperature returned to the initial temperature after 2.5 hours. So the strain response in tangent extended over 6 hours. And yeah, we can registered the maximal tensile strain accounted from the moment when the water was added in the cut, and this value reached 6.10 multiply -5 degrees. Then further, you can see the same graph, but for fresh clay sample. Here with maximal tensile strain accounted and reached 4.10 in -5 degrees. So as a main conclusion of this work, I can note following. So we proposed and implemented a new experimental technique for direct measurements of temperature deformations of such type of soils. The result of measuring deformations of frozen soils according to the proposed methodology can reveal the mechanism of stress-strain state formation for such soils in, of course, a wide range of thermal and mechanical loads. Also, the found and specified parameters of frozen soils can be used in consequent calculations using the FEM analysis for the goal of design the hydrotechnical structures in the Arctic conditions. Also, the results can be used for estimating stability of harbor and coastal engineering structures. So thank you all for attention.
Thank you, Artyom, for very interesting and informative presentation. Let us check whether we have questions on YouTube chat. Okay, I see we don't have. If some participants have questions for Artyom, you are welcome to ask them to YouTube chat, or somebody from our speakers may also ask some questions if you want. I see the question from Anna Barker. She asks you, what are the advantages of the technique for fieldwork applications?
Okay, thank you for this question. So the main advantages of this technique, it's a line in the area what we have very accuracy method for direct measurements of deformations on the frozen soil. So I can note two points on this question. It's a big accuracy and direct measurements. I mean on samples.
Okay, thank you for your answer. I see that we don't have any questions anymore. Thank you very much for your presentation, for your talk. We will switch on the next speaker. The second presentation is by Anna Novikova. She will present us the research dynamic of low-lying accumulative cost of Western Gedan Peninsula in the area of gas development. Anna, are you ready to give us a presentation?
Yes. Yeah.
Okay.
Good morning, colleagues.
Good. You can start sharing your screen and run your presentation, please.
One moment. Can you see it?
Yes, everything is
Yes.
correct. You can start.
Okay, thank you, Alexei. Good morning, colleagues, again. I would like to present you the study of Laboratory of Geoecology Ozonor of Moscow State University and the Institute of Environmental Survey, Planning and Assessment. And it's a study about dynamics of low-lying accumulative costs of Western Gedan Peninsula in the area of gas development. The coast of the Arctic seas claim special attention of the scientists due to their active dynamics with a tendency to retreat with an average rate about 0.5 meters per year. But most of the studies focused on the dynamics of erosional high permafrost coasts, so-called thermoabrasional. Given their high rates of retreat and evident tendency to retreat and relatively simple way to monitor the dynamics by tracing the retreating coastal bluff. Meanwhile, low-lying sandy coasts, so-called accumulative, in the Arctic region are not so well studied. I think I should say that we call such coasts accumulative, which means that these coasts are advancing gradient to the sea. However, in the recent decades, in the condition of Arctic climate warming and sea ice reduction, such coasts previously stable or advanced and also began to retreat. The erosion of these coasts may be triggered or intensified by the construction in the coastal zone. And accumulative coasts are especially sensitive to enhancing sea wave action and human impact as far as their low-lying surface composed by sands may be disturbed easily and may degrade faster compared to other types of the coast. In this work, we study an accumulative coast of the Gedan Peninsula. It is an eastern coast of the Ob Bay of the Kara Sea, and we study a 7-kilometer section of the coast between the mouths of the Haltanayaha river in the northwest and the Nadai-Picture river in the southeast. The area of study is a low-lying Holocene accumulative marine terrace. We call such surface slider, and it has about 0.5 kilometer width and high about 1 to 2 meters above the sea level. It is formed by a series of longshore beach ridges from 20 to 40 meter wide, separated by swales with a relative depth about 7 to 0.7 meter and a width from 20 to 50 meters. There's swampy and occupied by shallow lakes.
We see some rectangles which are obscuring the visibility of slide. Do you see the slides clearly? Because we don't see the parts of them on the upper, on the right side. Alexander, could you check? Is everything all right? Because I see that it's not clearly visible for the participants.
Well, it seems that in the offline version of the presentation, these rectangles are absent. So maybe it's something with translation.
Okay, Anna, could you please move the bars with the participants on the right side of your screen, somewhere down from the screen? Yeah, move them.
Yeah, you can see it.
We see them as gray rectangles.
Okay.
Yeah, that's much better. And the upper panel, if possible.
So now it's better. Okay.
Well, anyway, I think it's better than it was before. Please continue with your presentation.
Okay, thank you. So the beach and the slider are composed of fine homogeneous sands or loamy sands. The width of the beach from 2 to 30 meters. In some places, a low cliff is formed in the sediments that indicates recent erosion. The climate of the region is polar marine with average annual temperature about -10 degree. The range of water level fluctuation in the Gulf of in the area about 1.3 meters, depending on tides and surges. The maximum calculated annual sea level of repeatability one time in 50 years exceeds the average level by about 1.5 meters. That means that the flooding of Lida during high surges is possible. This part of the Kara Sea is covered by ice during 7 to 8 months per year. During the last decades, there's a tendency to rise of the summer temperature and prolongation of sea ice-free period, increase of storm frequency that are related to global climate change. And in 2014, within the study area, the construction of port facilities and ground infrastructure facilities began as a part of the Arctic LNG 2 project. And according to this project, the explored 7 kilometers of the coast will be almost completely occupied by the port and plant and infrastructure facilities. Our study is based on field and remotely sensed data. The field work was carried out in September 2020 and included a description of the lithology and morphology of the coast and geodetic survey of the coastline position and shore face profiles of the coastal zone using GGPS. Composition and structure of beach and wider sediments were described, and also we registered traces of technogenic impact. The data on the coastline dynamics we obtained using multi-temporal satellite images. We used 4 images with the spatial resolution 0.5 meters from 2012, 2014, 2017, and 2020 years. These images were punch-up, rectified, referenced, and interpreted. We traced the shorelines for the different time periods and calculated the rates for the automatically built transects over every 50 meters along the shorelines. And we are moving to our results. So we found out that during the last 8 years, for the period from 2012 to 2020, the studied coast experienced erosion at an average rate of minus 2.7 meters per year. That means that over these 8 years, the coastline has shifted landwards by more than 20 meters. The maximum retreat rates of 12 meters per year observed in the area to the south of constructed terminal, where the total retreat for 8 years amounted from 60 to 90 meters. But with all the background of general trend to retreat, some segments of the coastline in certain periods shifted toward the sea, like in the south. So the first studied period, 2012 to 2014, is a period of relative stability or even accumulation before the start of construction. 3/4 of the coastline shifted seawards. The entire coast aggraded at an average rate of 4.1 meters per year. It is inappropriate to extrapolate these values to longer time interval because it was obtained for a short 2-year period, but nevertheless, we propose that this period represents a normal natural evolution of these coasts. I mean, before the beginning of the construction, this coast was stable or even advancing. 2014-2017 is a period of sharp intensification of erosion, and this is the initial stage of construction. The situation became opposite in comparison with the previous period. On the 3/4 of the coast, we observe erosion. The coastal retreat rate averaged 5.8 meters per year. The most intensively retreating section was the 2-kilometer long section in the middle part of the study area on both sides of the constructed terminal. Average erosion rates here were more than 15 meters per year and up to 28.5 meters per year. Within this area, on the space images, we can see the traces of sediment excavation from the beach and tide flat. And during the last 2017-2020 period, the erosion is continuing, but with lower rates of retreat. Erosion was observed on the 2/3 of the coast. The average along all the coast rate of retreat amounted 3.8 meters per year, and the erosion rate decreased in the most intensively retreating area between the projected northern ice protection structure and the constructing LNG plant, which indicates a relative stabilization of the hydrodynamic processes after intensive impact at the previous stage. However, this is the area where coastal erosion threatens infrastructure facilities. In September 2020, the actively used road turned out to be a distance of up to 13 meters from the coastlines. That means that the coastal monitoring is necessary here, and dredging and sediment excavation from the beach must be limited. And if erosion continues, artificial beach nourishment is needed. So the maximum rates of retreat were observed during the years of intensive technogenic infrastructure restructuring of the coastal zone. This is the period from 2014 to 2017, and especially in the area of dredging and sediment excavation from the beach and tide flat. It's about 100 meters sweep zone along the coast. The construction of the southern of two ice protection structures began in 2020. Here you can see the projected ice protection structures. The structure will partially protect about 4 kilometers section of the coast from waves. However, erosion can be expected at the segments where the ice protection structure approach the coast, because current velocities there will increase. The most actively eroded section is located directly opposite the entrance of the water of the port between two ice protection walls under construction. The configuration of ice protection structure provides probable erosion of this section of the coast under southwesterly winds wave action. Also in the study area, it is the southwestern winds that contribute to the surge phenomenon. Therefore, despite the decrease in the intensity of waves in the inner water area of the port, it is necessary to monitor coastal processes in the area, especially in the area most vulnerable to erosion, and if necessary, to provide beach nourishment. So to conclude, the 7-kilometer section of the West Pitang coast was classified as stable or cumulative until 2014. The construction of port facilities and the LNG plant, which began in 2014, led to changes in the hydrodynamic system. In 2014-2017 period, the coastline shifted landward at an average rate of 5.8 meters per year, and in 2017-2020 at 3.8 meters per year. The receipt of the coast is caused chiefly by sediment excavation from the coast and by dredging in the nearshore zone. The construction of ice protection structure is planned in the project. Therefore, the retreat rates in the southern part of the investigated coast will decrease, except for the areas where ice protection structure come to the coast. To reduce coastal erosion, we recommend to limit excavation of the sediments from the beach and tide flat, and especially in the most intensively irrigation parts of the coast. They include the section to the northwest of the port, which will not be protected from the waves by ice protection structure, segments where ice protection structure approach the coast, and the most intensely eroded area between the northern ice protection structure and constructing LNG plant. To carry out coastal monitoring, paying special attention to the intensely retreating coastal section, and if necessary, to undertake beach nourishment in the areas where the infrastructure facilities are located near the coastline. For example, the most intensively eroded area between the northern ice protection structure and construction LNG plant. That's all. Thank you for your attention.
Thank you, Anna, for presenting your study. It's very interesting, very informative, and very fresh, and dedicated to recent field studies, as far as I see. So, okay, some questions. We have one question from chat. Natalia Belova asks you, thank you, Anna. Is there a possibility that the coast will move towards the sea again after the completion of construction? And I would like to add my question to this and ask you, do you expect any attenuation of coastal erosion rates or acceleration of coastal erosion? So what are your forecasts for its behavior, its dynamics?
Thank you, Natalia and Alexey. Yes, this our goal, aim to try to make forecast, but it's a little bit complicated because at the moment the almost the entire coastline will be is reconstructed, and we don't know how it will look in the future, but I propose probably that retreat will stop after the finishing of construction of all these plant facilities. And but who knows, in the conditions of Arctic climate warming, probably the retreat may continue. So we should monitor, and we should collect more data, because now we have not enough data to make a long-term forecast.
So are you planning to continue the field research in this area?
Yeah, I hope so.
Okay.
It's interesting to see what it will look like.
Okay, good. Thank you for your presentation, and good luck with your further investigations. We are moving forward to our third speaker. Unfortunately, Fyodor Yurov is unable to present his study personally because he is a technical assistant in the room 1. However, he provided us with a pre-recorded presentation, so I will run it and we will be able to watch it. If you won't hear any sound, please let me know via chat.
But we can't hear it. There is no sound.
You don't hear it, yeah?
No.
Okay, let me just.
It's only me. I don't know.
Okay.
No, we can't hear it.
Okay. So you don't hear the presentation?
No. Maybe on YouTube they can hear it.
Okay, let me just fix this problem. Just give me 2 minutes, maybe less. Okay.
Okay.
I'll fix this problem. Okay, let's try again.
Yeah, now it's I hear, but very slow. Slow.
calculate the impedance of slope. So the proceed.
Okay, can you hear me? Is everything correct with my sound?
Yes.
I heard that there was some problem with audio, with sound of presentation. Please accept my apologies for this technical problem. We will fix it by uploading the pre-recorded presentation of Further Europe to the GeoConference YouTube channel, so you'll be able to watch it with sound, and if you would like to ask the questions, you may forward them to the email of our conference. So we are moving forward. The last but not least speaker is Chatvumi Ayanti Kaviratna. Are you here?
Yes, I'm here.
Very nice. So you are welcome for sharing the screen and starting your presentation.
Can you share the screen?
Yes, we can.
Okay, okay. Okay, thank you very much. Good afternoon, everyone. This is from Japan, and I'm Chatvumi Kaviratna, postdoctoral researcher from Shibasaki Lab. And my topic is environment sustainability of Arctic shipping through potential HFO ban areas along the NSR. Which is quite different topic than the topic discussed here because I'm focusing on Arctic shipping itself. So here is the agenda of today's presentation. Giving a brief introduction, as you all know, like because of global warming, there is a continuous sea ice formation, which give an opportunity for Arctic shipping, especially because of its potential for distance and time saving than conventional shipping route. Because of this reason, there is a continuous increase in cargo volume transported via Arctic route, especially Northern Sea route, as you can see this figure. However, due to increase of cargo volume and the number of transit, there could be some environmental impact on the Arctic sea area, especially because of cold temperature and different biodiversity. So the purpose of this study is to discuss about different emission control measures from Arctic shipping, especially considering the vessel-based emission generated from Arctic shipping activities. So as the emission control measures, in this study, we focus on two different measures, HFO ban areas and emission tax, which both are mandatory and regulatory options. First, HFO ban areas, in the sense it enforce HFO ban areas so that vessels cannot burn heavy fuel oil inside these areas during the navigation. And emission tax is enforcing emission tax for the emissions generated from the vessels. Although there are many studies available regarding the emission tax, not many studies focus on HFO ban areas, especially for Northern Sea route. Having said that, my research objective is to analyze the effectiveness of emission control measures to minimize the vessel-based emission to the Arctic sea environment. So we have two different measures as mentioned before, HFO ban areas and emission tax, and we analyze with two different objectives. First, to minimize the emission level, and secondly, to minimize the cost. So we consider these two objectives because with the minimizing emission level, we can focus on the mandatory or regulatory emission control measures, while minimizing cost objectives support voluntary fuel switching with the HFO ban areas. So as the sub-objectives, first we estimate the emission and cost of the voyage without emission control measures when navigating via NSR. And secondly, estimate the emission and cost with the emission control measures when navigating via NSR. There we consider two separate objectives, minimizing total emission and minimizing cost. Here is the entire analysis framework. For this study, we consider the navigation path, like individual navigation path of each vessel or each voyages, so that we do not consider representative path for the Northern Sea route. And also based on that, we collect ice condition data, mainly ice thickness and ice concentration. And depending on that, we decide the speed of the vessel as well as the ice impose cost. The ice impose cost, mainly the ice breaking cost, and also the additional capital and operating costs for the ice class vessels. And depending on the speed and the engine factor, we can calculate the fuel consumption, which directly influence on the cost of the voyage, as well as the emission level generated by vessels. In addition to that, we consider regulatory emission control measures such as HFO ban areas and emission tax. With HFO ban areas, we can discuss fuel switching, which means in this study, we consider the heavy fuel oil and marine gas oil as two alternative fuel types with inside and outside HFO ban areas. And then based on that, we can calculate the emission level because of different emission factors associated with different fuel types, and which help to discuss about environmental impact as well. So here is the entire analysis framework. And next, moving to the methodology session. Here, as I mentioned before, in this study, we consider the HFO ban areas for specific voyages, which means voyage-specific navigation length and the navigation path must be considered. Regarding the navigation legs and the zones, when considering previous studies, they mainly consider the 7 zones or legs along the NSR for the convenience of cost calculation. However, the majority of studies consider the same or average navigation speed for the entire route and do not consider specific navigation path geographically, rather assume representative routes along the NSR. In our study, we consider numerous navigation legs, about 150, and variation of navigation speed at individual legs. For that, we obtain the navigation path directly from AIS data, and then we create the grids covering this navigation path to calculate the navigation length inside each grid. So if this length less than 50 nautical miles, we consider it as a threshold for considering the navigation length or leg. And then if it is outside NSR, we consider 15 nautical mile as the threshold for considering the length of the navigation leg. So that our objective was to having shorter navigation length for the route segment within NSR, so that we can analyze the navigation speed within NSR more precisely. And then as for the potential HFO band areas, before deciding optimal location for HFO band areas, in our model, we decide potential HFO band areas, where we divide the entire navigation path into 17 areas given from A to Q in this map. And when deciding these areas, we consider distance from the coast and the previous navigation path, as well as the boundaries of our grids and some geographically highlights such as Novoselynia, as you can see here. And also we can consider the further improvement with the Russian navigation maps as well. However, we add this area S, which is outside the NSR, and some areas around Barents Sea areas. Although they are not within the NSR, we add these areas as potential HFO band areas to consider because of high density of navigation or ship location. And then as the scenarios based on sea ice condition along the navigation path, we consider 3 different scenarios: free ice, medium ice, and heavy ice scenarios. These scenarios are assumed based on the navigation path of specific voyages. For example, this is the distribution of the sea ice condition along this navigation path. So for that, we obtain the ice condition data from ADS Topaz forecasting system from July to December 2018. In this period, we consider, because in this study, we only consider autumn and summer navigation season. And then after collecting daily ice thickness and ice concentration data, we can calculate the 5 days average ice thickness level as given in this vertical axis. And then we multiply the ice thickness and ice concentration, because both have significant influence on the navigation along the NSR. And then the vertical axis, the horizontal axis indicate the location from left to right along the NSR. So when deciding the ice scenarios, here we decide the free ice scenario, medium ice scenario, and the heavy ice scenario depending on the time of the year. Like free ice scenario mostly from August, September, and the medium ice scenario from September to late October, and from it's like heavy ice scenario from November to early December. So these are the 3 scenarios that we are going to use in this analysis regarding the ice condition. And also for navigating through NSR with different ice condition, we consider 4 different ice threshold level, which are given from I1 to I4. So if the ice thickness level within a specific navigation leg is less than this level 1, so the vessel speed does not have to be reduced. So vessel can navigate with the same speed without reducing, because the ice condition is not that severe. But if it is between 1 and 2, the vessel speed in this particular leg must be reduced to a level defined by the ice thickness level. For that, we use this equation 1, 2, 3, which are depending on the design speed of the vessel as minimum speed of the vessel and minimum and maximum ice threshold level. And then if it is between level 2 and level 3, we assume vessel need icebreaker assistance, and the speed of the icebreaker is 12 knots. And if it is between 3 and 4, vessel navigate with icebreaker assistance, still the speed is 10 knots. And then if the ice thickness level is greater than level 4, we assume vessel cannot pass through this particular leg even with an icebreaker. So these are the conditions for the navigation within NSR. And then here are the cost function. First, when calculating the total cost, we consider the capital cost, operating cost, fuel cost, and emission tax, as well as ice-breaking cost for the voyage. And the capital cost and the operating costs are calculated from equation 5 to 6, where we refer previous studies. And here, these two parameters indicate the premium of the capital and operating cost for the ice class vessel compared to the open water vessel. And then here, equation 7 calculate the fuel consumption, the total fuel consumption as the summation of the fuel consumption in individual legs. And the individual leg fuel consumption is calculated with the main engine, auxiliary engine, and the boilers as well. And for the fuel consumption calculation, we follow the IMO 4th greenhouse gas emission study with admitted formula, where we consider the differences in the draft as well as the speed as well, in addition to other chlorine and weather correction factors. And also we consider the engine load and the impact on engine load on the specific fuel consumption when estimating the total fuel consumption of the vessel, which is also depending on the power demanded by vessel when it is navigating at a particular speed. So this is for the fuel consumption by the main engine. And then these are the cost function for the emission tax as well as the ice-breaking fee. So for the emission tax, we consider the four different emission level emission types: CO2, CH4, N2O, and black carbon emission. And with their different emission factors related to fuel types as well as global warming potential to convert them into carbon dioxide equivalent. And also we consider the ice breaking cost following the Russian regulation on ice breaking cost calculation. And this ice breaking cost is applicable only for legs that have ice thickness level greater than the maximum threshold of independent navigation. And here is the optimization problem to decide the location of HFO ban areas. For that, we consider two separate objectives as mentioned before as alternative scenarios. First, to minimizing the total cost, and secondly, to minimizing total emission, which are given from equation 13 to 14. And the decision variable HFO ban areas is given here in equation 15, and the maximum allowable HFO ban areas are given by equation 16. And in addition to that, we also consider the sulfur SOx constraint as a fraction from total fuel consumption to minimize the sulfur emission using this methodology. Then here are some vessel and voyage specific input data for this particular, the developed model we tested with one voyage, which is given in this map. And then according to our calculation, there are 13 legs before the NSR, and from 31 to 127 is within the NSR, and then after NSR, there are some legs until the 147, and these are the associated HFO ban areas for this particular voyage. And also these are the threshold level that we assume from I1 to I4 for our calculation. And there are some voyage and vessel specific input data. You can see gross tonnage, lifetime, and other input data for the specific voyage. And these are some model specific parameter for our calculation and with related references. And also some market specific parameters, including the fuel prices and emission tax and other emission factors as well. And this is the ice condition for a specific voyage. This is ice thickness and the ice concentration that we use as input for our calculation. So this indicate the ice this particular voyage and particular navigation length, the distribution of ice thickness and ice condition. Next, moving to results and discussion. So according to our calculation, we could, if we summarize the benefit of HFO ban areas and the emission tax, we can see there is a significant reduction of the CO2 emission as well as SOx emission after implementing HFO ban areas, depending on the ice condition scenario. And the least emission level observed for medium ice scenario, possibly because of the lower average speed level than the free ice scenario due to the presence of ice, and lower speed than heavy ice scenario because of not using icebreaker as much as similar to the heavy ice scenario. And also we observed increase in the total cost with medium ice and heavy ice scenario than free ice scenario due to the icebreaker cost as well as the higher speed with the icebreaker assistant. And also the significant reduction of the XOX emission could be observed, especially during the medium ice scenario, according to our calculation. And here the characteristic of voyages based on the ice condition, there we could observe the average speed within the NSR and medium ice scenario derive the least average speed, and before NSR navigation speed in average is highest one. And also here is the selected HFO band areas between two objectives when minimizing cost and minimizing emission. Lower number of HFO band areas are selected with minimizing cost objective, and the highest number selected with the minimizing emission objective. And also we analyze the sensitivity of maximum SOx emission, which as a fraction of total fuel consumption. And when changing this constraint, we could observe if we have very small number of very small value for the SOx constraint, there is a difference between number of selected HFO band areas between three ice conditions. And there, if we consider about the total COE emission, we can see the carbon dioxide equivalent, the least amount is derived from the medium ice scenario when compared to free ice scenario and the heavy ice scenario. However, very high level of XOX fraction is not suitable because it will not reduce the emission level after some time. And also we analyze the sensitivity with the maximum available HFO band area. So according to that, we could observe a clear trade-off relationship between the cost and emission objective, as you can see from these figures. And still the free ice scenario has the least cost because of absence of ice breaking cost as well as the extreme ice condition and the impact of the ice condition. However, we can see the highest cost and the highest emission HFO band areas and emission levels is related to the heavy ice condition, which is similar to the previous objective. And with the minimizing emission objective, we summarize the order of selecting HFO band areas. This map indicates this number indicates the order for selecting HFO band areas, where the area H has the highest priority and area G has the least priority, possibly due to the navigation length within area H is the highest, and also the average speed is higher, and the area G has the least navigation speed as well as the least navigation length. So this is the order of selecting HFO band areas. And then also we compare the HFO band area selected with the three ice condition with minimizing total cost objective. According to that, although this area H and C are selected as HFO band areas in all scenarios, the selection of other areas depending on the ice condition, and also the location of HFO band areas are varied between the minimizing cost and minimizing emission objective, which support the mandatory or voluntary fuel switching policy. So as the conclusion from this study, so we analyzed the effectiveness of enforcing HFO band areas and emission tax for enhancing the environment sustainability of Arctic shipping, and optimum location of HFO band areas with both minimizing emission and minimizing cost objectives are observed. And also according to the results, we observed partial variation of HFO band areas among three ice conditions: free ice, medium ice, and heavy ice condition. And also medium ice scenario generate the least emission level according to the results. And finally, the total cost was increased due to the fuel switching from HFO to MGO, as well as the impact of the emission tax. So as for the future work, we will enhance the designing of HFO ban areas with Russian Arctic zones, because this is something very important for the results, as well as we design the HFO ban areas considering multiple voyages simultaneously, which enhance the practical implementation of such kind of policy. So having said that, I'm going to wind up this presentation, and these are the related references, and thank you very much for your kind attention.
Thank you. Thank you very much for your presentation. We are searching for questions in the chat of YouTube. So far, no question, but maybe someone would like to ask them. Yeah, just maybe other speakers would like to ask a question. What about Anna? Do you hear us?
Yes. Yes. No.
No questions.
No.
Okay, just let us wait for maybe 20 to 30 seconds more. Maybe some questions appear in the YouTube broadcasting.
Okay.
Yeah, maybe I have a question. So I'm not an expert in legislation in North Sea routes, but according to your presentation, I see that you propose more efficient way to design these routes. So who will benefit from these actions? Who will benefit from this optimizing measures? Maybe some countries or corporations or vessel owners.
Okay, thank you very much for the question. So basically, even International Maritime Organization, they are trying to have like emission control or areas or the change in the fuel types because of the environmental concern for the entire globe, like to reduce the negative impact from the global shipping. But in case of Arctic shipping, it is more serious because of the cold temperature and the very different biodiversity related to the Arctic Sea areas. That's why it is important to have some measures to control the vessel-based emission, because still this route is not using optimally. But if in case if they use in the future, there should be some mechanism to control the emission level to make sure that the sustainable shipping, especially considering environmental impact and the impact on the Arctic Sea areas and the people living there.
Okay, thank you for
Okay.
for detailed answer. I see that there are no more questions. Okay, I think that some participants who are unable to participate to attend our session due to time difference, so they will be able to watch our session in recording on YouTube channel, and maybe they will have some questions. If you have any questions, please ask them to our forward them to our email, and please indicate the speaker who you are asking to. So we are at the end of our session. Thank you everybody who participated, who asked the questions, the speakers, and all attendees of our session. The next session starts in room number 2 in noon. This is session number 9, so all the speakers and conveners are welcome to enter this room 15 to 10 minutes before it begins. Now we have 40 minutes break. I hope you will enjoy it, resting from the presentation. Okay, thank you.
Thank you very much.
Thank you very much.
Bye-bye.
Bye.
Bye.
Hello.
Hello, Professor Tukri.
Hello, hello.
Yeah, nice to meet you.
Nice to meet you as well.
Yeah.
Hello. So is Moscow hearing us? Okay, no. I can see that Brandon is here, so your talk is at 1 o'clock, and now I'm talking about Moscow time. But I think that's the same time. No, it's not. It's not the same time than in South Africa. No, it's 1 hour difference in summer. Exactly.
Yes, I'm an hour ahead at the moment.
Yes,
Sorry,
Vladimir Yakinov, I think I can see you. Yes, nice to see you. So your talk is at 12:40. And then Sankyu Yeon, we already said hello. So you are starting. And then there's another one, the fourth paper. Seong Yeong, are you here? Okay, so your is the second paper. How about the first?
Yes, I'm here.
Okay, so you are the first speaker. Okay, good. So all the speakers are here. My name is Jukka Tuhkuri and I will chair this session. But we have 5 minutes still to go. Dr. Yeon, I mean the first speaker, could you please check if you can share your screen?
I will try. Here comes share. Can you see the screen?
Yes, we can. So that's good.
Okay.
So that's good. So that part works. My computer says now that it's 12 o'clock. So welcome to this session, Ice Loads and Vessels 1 on POAC 21. And I hear you can all, I hope you can all hear and see this session. We have 4 papers on ice loads on vessels. And sorry, my name is Jukka Tuhkuri. I'm from Aalto University of Finland, and I will be the chairman of this session. So we have four papers. There's a time lot for 20 minutes for each. I hope the presenters will stay in 15-minute presentation, and then we have 5 minutes time for questions. And the first one will be given by Sang-Kyu Yeon, numerical simulation on the ice load acting on Aron using damage-based erosion model. Please.
Okay, thank you, Chairman. My name is Yoo Kim from Inha University of South Korea, and this talk was originally supposed to be delivered by the first author that you see here, Mr. Sang-Kyu Jeon, but we changed our plan. So second author, myself, will do presentation. Today, I'm going to talk about numerical simulation on the ice load acting on Aron using damage-based erosion model. I will start with some introductions. As you know, ice load is difficult to know due to its complicated physical behavior. Estimation method of ice load may be divided into 2 different methods, and they are experimental approach and numerical simulations. Experimental methods can further be divided into full-scale measurement and model-based test. Full-scale measurement is most reliable one, but as you know, it requires time and cost, and sometimes data collection is not very easy due to the many restraints frequently met during actual voyage. Model test is very good alternatives for ice load estimation, but it also has some limitations such as time and cost. So not very practically feasible to everybody. Numerical simulation is another good way to estimate ice load, which is rather cost-effective compared to the experimental ones. And also parametric studies can be easily done, which is quite important to understand the characteristics of ice load. Here is some previous studies. Ice load, there have been numerous studies covering numerical method for isostructure interactions, and I will talk some of them in this slide. In the case of unbreakable ice, discrete element method is popularly used because we only need to calculate the rigid body dynamics of ice flows colliding with the structure. But when it comes to the breakable ice, such as level ice, situation becomes more complicated because we have to focus on the accurate simulation of ice fracture. Figures on the right side show some examples of numerical methods which are used for the fracture of level ice colliding with a conical structure. Here you can see extended finite element method and also use of cohesive element and also discrete element method. Lower right one is a traditional finite element method with element erosion technique. And in this study, we further developed this element erosion technique by combining it with continuum damage mechanics to improve the accuracy of simulation result. Now I will talk about some theoretical background of our simulation method. Material modeling is, of course, of utmost importance when it comes to ice fracture simulation. In our study, ice was modeled by combining classical Drucker-Prager plasticity and damage mechanics. This slide summarizes this well-known plasticity model, I mean Drucker-Prager model. The Drucker-Prager yield criteria is generally used for materials which are affected by hydrostatic stress, such as soils, rocks, and ices. Upper figure shows that yield surface is in the shape of cone in principal stress space, which means that material yield easily under hydrostatic tension condition. Linear means that the relationship between hydrostatic stress and deviatoric stress is linear, as lower left figure. As I said earlier, damage model was combined with the Drucker-Prager yield criteria to define the value of ice in brittle way. The upper figure is a general damage model that includes hardening and softening after damage initiation. In order to simulate brittle nature of ice, general damage model shown in the upper figure is modified as shown in the below figure. For damage model after yield, two parameters need to be clearly defined, and they are damage initiation and evolution. For brittle behavior of ice material, damage initiation was assumed to start right after initial yield, and load carrying capacity was set to drop suddenly so that material fails in a very, very brittle way. Right after damage is initiated, damage variable D, capital D, start to grow and evolve with damage and ultimately becomes 1, which means that material completely failed. For damage evolution, a fracture energy concept was introduced. For this, damage was assumed to increase linearly as the plastic strain develops within the material. And this relationship is defined by the fracture energy. This slide is how local crushing failure was realized in our numerical simulation. Crushing is continuous breaking phenomenon, which is difficult to be realized in discretization-based numerical methods, such as finite element method. As you can see in this figure, you can expect the vessel will freely run when element erosion technique is applied. To avoid this troublesome situation, we allow the structure to penetrate into the ice material so that crushing is taken into account implicitly. When the structure penetrates into the ice, it is governed by a pressure penetration relationship, which is shown in the middle. Upper limit of this pressure penetration curve is said to be the compressive strength of the ice material, and slope of this initial stage need to be defined properly. Next, thing is about buoyancy and drag. For buoyancy, hydrostatic pressure was applied for all elements. I mean, the elements that comprise level ice residing below free surface. Special treatment was used to maintain the buoyancy force even after elements were eroded. Drag force, which is assumed to be proportional to the velocity of the element, was applied as well. From now on, I will explain the modeling process and result of the simulation for the level ice and Arctic vessel interactions. The Aran model ship and level ice was modeled according to the experiments carried out in ice tank of Kuriso in South Korea 2016. In this model, Aran voyages through level ice, which is 32 meter long and 30 millimeter thick. Model ship is 5 meter long and 1 meter wide. These figures come from the scale ratio of 19:1. Model ship was modeled with rigid element and levelized with deformable solid element. As explained before, damage-based erosion model was used for the level ice. You can see some material properties in this table, some of which were quoted from previous studies. Ice was properly restrained to prevent rigid body motion during the collision. So under these conditions, simulation was performed for 3 different forward speed cases. This is the simulation. I hope this video works.
It started, but then it stopped.
Okay. What's wrong? Okay, let me just move on. This is simulation result of a certain particular forward speed case seen from 2 different perspectives. Without video, I cannot explain things. I will skip to the next slide directly. So upper left figure here shows the actual crack pattern that occurs when the bow of ship and level ice collides. And you can clearly see that ice breaks in the shape of which is formed by radial and circumferential cracks. In our simulation shown in lower part, radial cracks are generated first, then the circumferential cracks develops as a result of bending failure of divided level ice. As you can see in this figure, the pattern of radial and circumferential crack are identified at initial entering stage as well as continuous breaking stage. Okay, this guy does not work also. Okay, for this we have an additional picture in the next slide, so I will move to next slide. Okay, it moves. Oops. This is top view of simulation result. Lower video clip is animation of crack formation during continuous breaking stage. Here, red line represent cracks. As you can see, formation of a radial and circumferential cracks is continuously repeated, and the shape of ice flake is wet or curved trapezoid. In order to check the speed dependence of ice flake size, we calculated the radial length of ice flake size as shown in this figure. Ice flake sizes were measured all broken ice flakes, and the probability distribution were obtained by statistical analysis, as you can see in the middle. And it was confirmed that both average and variance of flake size tend to decrease as the speed of ship increases. As you can see on the right figure, the average ice flake size of numerical simulation is a bit larger than that of experiment. However, A decreasing trend with respect to the shift speed was seen in both simulation and experiment. Okay, now I will talk about isoresistance. Isoresistance may be decomposed into 5 different components, as you can see on top box. And these components may be regrouped into 2. One is braking component, and the other one is emergent component. We try to divide the numerically obtained total isoresistance into 2 components and compared it with numerical result. Isoresistance decomposition in experiments and numerical models are different because of the different nature of each method. So in case of experiment, the pre-zone test result was used. You can see pre-zone test in lower left figure. By this, braking resistance can be obtained by simply subtracting total resistance by pre-zone resistance. This, of course, is approximate approach because pre-zone resistance does not necessarily mean a submergence resistance. In our numerical analysis, braking resistance was obtained by running rubber removal model separately. You see this animation still not working. Okay. So in this model, rubbers were removed from the analysis right after braking failure occurs so that only braking resistance was calculated. Then the submersion component was obtained by subtracting this braking resistance from the total resistance of original model. The wrapped figure is the mean ice resistance which we got from simulation and model test. Total resistance estimated by numerical simulation matched quite well with the experimental result for 3 different forward speed cases. The figure on the right is a graph comparing the contribution of each ice resistance component obtained through simulation and model test. Blue is a simulation result, red is model test result. Even though total resistance magnitude are similar between the 2, component by component comparison is not that good. I think this is caused by the assumptions that we have made in the beginning about a pre-zone resistance, which is not expected to match precisely with the submergence crack. Finally, we try to calculate some local ice load acting on external ship hull. As you know, the bow of icebreaker is the path of direct collision with sea ice and is the subject area of fatigue analysis. Sorry, I have to. So in order to figure out the distribution of peak load and peak frequency occurring near the bow, 15 panels were arranged along the ship external hull within the range of 1.3 meters from bow near the free surface. Local ice load was analyzed using 2 different models, one with level, one without level. You remember that we have 2 different models, with level and without level. So as an example, two road time histories are plotted here, which was picked from the panel highlighted in yellow circle in the bow area. As you can see in the rubber removal model on the right, you can see the typical pattern of the load induced by braking only. It is in the form of well-separated triangle impulse with a very short rise and decay time. On the other hand, road time history from original model shows that individual impulse overlaps a lot, so that load level rarely drops to 0, which is not the case of a rubber removal model. From this, we obtained a probability distribution of both peak load and peak frequency. The red line is mean of peak, the blue bar is peak frequency. As for the overall trend, you can see that the highest peak frequency occurs at the far front of the bow, which is panel number 1. And you can expect it from the beginning. And looking at the mean of peak, it tends to decrease as you move away from the bow in the original model. On the other hand, this mean of peak of rubber removal model slightly increased at the end of the panel array. And we think this is caused by the increasing flare angle as you move away from the bow. So flare angle becomes its maximum around panel number 15, which is the shoulder part of the ship. Okay, the conclusions. Here, ice load acting on the around model ship was calculated by applying proposed simulation technique and compared it with the result of model test. And also both braking and submergence ice resistance was successfully decomposed, and expected contribution of both components matched well with the previous study results. Distribution of the mean peak load and peak frequency was derived, and the tendency was analyzed. And this result can be directly employed in the fatigue analysis of Arctic vessels. Sorry, I didn't move slides. Okay, this is the end of my talk. Thank you.
Thank you very much. That's an interesting presentation. Are there any questions? I'm trying to look at the chat in the YouTube, but I don't see there any questions. Are there any questions from the people in the Zoom room? If not, then I have one question. I think we have time for one question. I thought it was really interesting that you were looking at the kind of the classical composition of ice resistance through the simulations, but I didn't fully understand. I mean, you had some differences with kind of the model scale data and your simulations, but can you go back to that slide, if possible, and kind of a little bit explain a little bit more what exactly, what do we see there, and why is that? I mean, that so the braking component in the simulations was much smaller than in the experiments. Is that so?
Yes, correct. So we have thought, we have tried to find some reason for this, but the conclusion that we derived by looking at this is that Frisson test does not exactly match with submergence resistance. That's what we actually have thought of, because when you do Frisson test, you have to arrange Frisson pieces of ices on the free surface with a certain size and shape, which is not quite exactly same as what actually happens in ice breaking process. And also during Frisson test, I expect there is a piece-to-piece contact between ice pieces, which also is not something that you expect from real world situation. That's my explanation on this discrepancy.
Yes, that sounds reasonable to me. Yeah, thank you very much. Thank you very much. And I think you need to stop sharing, and then the next speaker, Dr. Jeong, can start sharing.
Okay.
Perfect. Now we can see your screen. Yes. Okay. Now, okay. So
can you hear my voice?
I can hear your voice. I can see your slides. Please go ahead, Dr. Jeong.
Okay, thank you. Thank you, Chairman. Good morning, afternoon, everyone. My name is Seongyup Jeong from Korea. I'm working for the Korea Research Institute of Ships and Ocean Engineering. The thing that I want to point out today is ice road characteristic acting on the ship hull. To further understand the effect of ice road on the ship, the model tests were carried out in crystal ice tank, and the distribution of ice road will be discussed in this presentation. The outline of presentation like this. First, I introduce the background of this study, and I will describe the model test in an ice tank and test result, and I'll summarize a few principal things in this study. You know, the dramatic reduction in the Arctic sea ice cover has increased the opportunity for the shipping activity in the Northern Sea route. Especially, there is a great boost of shipping activity in the northern west part of the NSR because of the Yama LNG or Arctic Energy 2 project. So ice road is a matter of considerable importance for shipping operating in ice-covered waters. In particular, understanding the ice road acting on the ship hull like this can provide useful information about the structure safety and the icebreaking efficiency. So it is a major concern in the modern ice-going ship design process. Therefore, the intention of this study is to improve the physical understanding of ice road distribution during the ship and ice interaction process. Especially, the ice model testing is used to predict a ship performance in ice at the early design stages so that it can provide valuable data such as distribution of ice road and ship resistance characteristic in ice-covered waters. So in this study, a series model tests were performed in Chris Ice Model Basin. In addition, the distribution of ice road in river ice and pre-zone ice and ice-rich conditions are discussed. The main study has been conducted to understand the ice road acting on the ship hull. For example, Johnston et al. Presented the global load obtained from the horse in motion using an inertial measurement system called MOTON on the US Coast Guard Healy and the Canadian Coast Guard Louis H. Laurent and validate the MOTON system with a ship model of Canadian Coast Guard Terry Fox. Professor Kujala analyzed the ice crossing pressure on the ship hull to improve the understanding of the physical process of ice breaking at a model scale using a tactile sensor like this. In addition, the ice bridges are a very difficult obstacle to the navigation of ice-going vessel in ice-covered waters. So Kalmaz analyzed ice roads that occurred during an ice-rich ramming test with icebreaker Oden, and Kruliana et al. Studied the ship performance in ice-rich condition and developed a performance prediction model like this. In this study, the model tests were carried out at the Chris Ice Model Basin, and the model C was icebreaking research vessel. The name is Around, and she is the first Korean icebreaking vessel with a KI class designation icebreaker for LATAN. The ship's main particulars are given in these tables, and the model ship was a bare hull without its own propulsion unit. So ice test was performed with a towed ship model. In addition, 6 tactile sensors were installed on the ship hull around the waterline area of the port side, like this, to provide information about ice road distribution. The tactile sensor should be calibrated to convert sensor output to ice rods. So calibration procedure was conducted before the ice test. From the calibration test, the relationship between the applied load and sensor output and calibration factors can be determined. This figure shows the result between the value of the ice road obtained using the tactile sensors and one-axis dynamometers. This is right variance, but the ice road measured with the one-axis dynamometers agree with the calibrate ice roading obtained using the tactile sensor like this. To investigate ice roading during the ice breaking process, the model test was carried out in river ice and pre-zone ice and ice-rich condition. The test conditions are summarized in this table, and during the test, the density of the model ice was about 880 kilogram per cubic meters, and the friction coefficient between the ship hulls and model ice was about taken as 0.05 during the test. This slide shows the ice-rich formation process. The preparation of ice-rich is composed of 3 phases: ice cutting and breaking of the ice into flows, and forcing the ice seat and arrangement. Generally, the ice-rich formation was modeled according to the recommendation of the ITTC in this study. The total 3 ice tests were conducted, and the mechanical property of the model ice was measured according to the recommended procedure of ITTC. This picture shows some kind of the friction measurement, and this picture shows a punch test to measure the shearing strength of the ice ridge. As can be seen in these video clips, the interaction between the ship and ice is a very complex process. Ice flows tend to rapidly increase when the ice interact with the ship's speed. And when she moves in four direction, an ice sheet can be broken around the ship's surface. The effect deflection of ice sheet related to the fracture failure of ice. The distribution of ice load are shown in these figures. The high loads occurred at bow and shoulder sections in straightforward mode. In particular, the rotation of broken ice flows frequently occur around sensor 3 like this, so large ice load were obtained during the test. The mean ice load presented increasing tendency with the increasing ship speed. A relatively high ice load at the stern area was observed. In addition, the ice load at the midship section depends on the friction between the broken ice floe and ship hull surface, so magnitude of this load was not rosy in the test. The difference in the ice load between the bow and the midship were about 30 newtons according to the increasing model ship speed. This slide shows the ice load distribution in the Frisson ice case. The results were similar to those of level ice condition. It was observed that the magnitude of ice load in the level ice was approximately 50% higher in both sections, and that of Frisson ice at the speed of 0.595 meter per sec in full scale condition about 5 knots because of the ice breaking resistance component. In particular, the ice breaking resistance is the largest portion of the total ice resistance. It can be directly obtained by subtracting the Frisson ice resistance from the corresponding ice resistance in level ice. This video clip shows the ice ridge penetration process. During the penetration, the magnitude of ice load related to the risk of structural damages. So ice load due to the ridge penetration could affect the global and local structural strength of the model hull. In addition, the magnitude of ice load are influenced by the ice fragment size and the spacing of the ridge keels. As shown in these videos, the ice fragment was split and submerged around the ship bottom during the ridge penetration. Therefore, the magnitude of ice ridge loads depends on the ship location around the ice ridge cross-section area. This figure shows the magnitude of ice load obtained from the tactile sensors. The large ice load occur at pitching situation, and the highest ice load occur when the bow penetrates the ship deepest area point of the ridge keel. Therefore, the bow impact could influence the ice load significantly. The highest ice load at the bow section, about 136 Newton with a modest speed at 0.119 meter per sec. In the full scale condition, about 1 knot. In addition, the high ice load occur in shoulder area, and the ice load at the failure area were lower than those of the ice load at the bow section during the test. Furthermore, there was a partial impact with a big ice fragment at the stern section, but the magnitude of ice load was relatively smaller than that of other locations during the test. This is my last slide. Generally, ice load influence the ship structure and ship performance in ice. Therefore, the design concept requires knowledge about the magnitude of ice loading on the ship hull. That is why we focus on this issue. In the level ice, the relatively high ice load were observed because of the bow and shoulder crossing and buoyancy and friction force around the failure section from the interaction between the ice floe and the ship hull. And the magnitude of ice load shows a decreasing trend around the ship longitudinal direction in forward direction mode. When the ship broke broke through the ice ridge. The highest ice road occur at the four regions due to the crossing and sealing failure mode of the consolidated layer and ice rubber. And the number of large ice road spike occurred at the shoulder and midship section as well, due to the buoyancy and friction force between the ship sole and ice fragment. That's in my presentation, and thank you for your attention, and your questions are very welcome.
Thank you very much. Again, I'm looking at the chat in the YouTube channel, and I don't see there any questions or comments. I hope I'm looking at the right place. Are there any questions from the Zoom room?
Yes.
Please, thank you.
Hello, John. Thank you for your interesting presentation. So I have the following question. So you, in your study, in your presentation, you used the term mean load. What does it mean? Is it a total contact force, total interaction force? And is it possible to obtain, based on this value, for example, the ice pressure, the form of ice pressure distribution, and other parameters, ice load parameters, excluding the total contact force?
Yeah, thank you for your question. And you know, the shear resistance in ice is related to the contact area during the ice breaking process. So we have to know the contact area during the ice breaking process. But in this study, we focused on the mean ice road to determine the ice road during the ice road around the water area during the test. So in this study, we focused on the normal, the average ice road, but the future study will focus on the maximum and the lower ice road regarding to the contact area. So this research will be further, this study will be, it will be future work, but in this area, so I just focused on the average first.
Thanks.
Yeah.
I could follow on that because I'm sorry, but I did not fully understand your reply. So average in what sense? Areal sense or time-wise? Because you showed those histograms of loads. So what really they were?
So in the test, we knew the tactile sensors. You mentioned that we can define the contact area during the ice breaking process, and then we detect contact area in the ice road at every time phase. But there is a lot of data sets. So in this study, we will just focus on the time averaging, measure the ice road data during the ice breaking process. So we summarize the average ice road data during the test.
To one tactile sensor.
Yeah, especially we installed 6 tactile sensors like this, and then we summarize the ice road data every sections like that. So this is the model ship speed in 1 knot and 3 knot and 5 knot in the full scale condition, and this is the sensor area location in 6 area. And this is the first one sensors, and the last sensor is over here.
Yeah, okay. Okay, very good. Very good. Any other questions or discussion? Maybe we kind of wait for a few minutes if somebody wants to join this room before we go to the next talk. So if you have any other comments, please, because we have 2 minutes time.
Dear colleagues, I think right now the following speakers can check the presentations if there are no questions while we are waiting.
Exactly, that is very good. Exactly, that's very good. So Vladimir Yakimov, maybe you can, or could you please, Dr. Yeong, if you can stop sharing, and then Vladimir, you can start sharing. We can check if that works.
Okay. Did you see my presentation? Do you see my presentation? Yes.
Yes, very well. Works fine. Thank you. And I can hear you as well. I think you can start now. I think we are close enough to 12:40. So please, Vladimir, please start.
Good afternoon, dear colleagues. I hope that all of you are in a good mood and a good health. Let me introduce my presentation on subject determination of design ice slots on ship hull using specialized software prepared in cooperation with my colleagues from the Viborg Shipyard and Peter the Great Polytechnic University. So, it is known that the ice strengthened structures of ship hull have to accept and to withstand the appropriate design ice loads, and therefore the correct estimation should be treated as a priority task. So, how could we determine the ice-induced loads acting on ship hull, design ice-induced loads? So, there are two main interlinked approaches. The first one is regulatory calculation, which is implemented according to the currently valid requirements of national or international regulatory documentation. This documentation could comprise, for example, the requirements within the rules of different classification societies. For the second is the structural requirements within the unified requirements of the ICS, and for example, the other specific requirements within other standards, codes, guidelines. And the second way is the direct calculation, which is implemented involving the methods based on physical models for mechanical interaction between ship hull and ice cover. So this approach could be divided into two main interpretations, the deterministic interpretation and the probabilistic interpretation. All of these approaches, all of these calculations could be implemented using specialized software, but in this study we will regard only this one part, the use of specialized software to calculate the ice loads with the use of direct calculation methods. I will not stay at the theoretical backgrounds, advantages and disadvantages of regulatory calculation of design ice loads on ship hull, because they are conducted according to the rules, and the most problems, most issues are clear in this way. I want to mention only the software products which are used in the Russian engineering practice to realize this topic, this goal. We could use two types of software, there is the specialized program models, which are integrated into large and complex software systems to perform computer-aided design and check calculations. For example, there are the software solutions Ruslan, Istrix, and Marsals. And there are available also the software applications we are focused exclusively on determining of the ice loads on ship hull. It means that they use only for calculation of ice loads. Here you can see the conventional typical example of regulatory calculation of design ice loads on ship hull. Here you can see the diesel electric icebreaker and the distribution of ice loads lengthwise and height-wise the ship hull. But the alternative way is the determination of ice loads on ship hull involving the direct calculation methods. First of all, this method we should use, for example, for a large tonnage oil tankers, gas carriers, or for large powered icebreakers, the ships which found wide application at the present time. And these methods are based on physical models for mechanical interaction between ship hull and ice cover and directly take into account the specifics and details of a particular interaction process. It means that we could take into account the actual conditions of ship navigation in ice. For example, the navigation water area, the navigation season, the state of ship loading, the trajectory, direction, and speed of ship motion in ice, the type of ice cover, its different characteristics, such as geometric, mass, physical, and mechanical. And the important factor that the ship, in this case, could have initially any dimensions and hull form. So here you can, on this screen, you can see the development of national software for direct calculation of ice loads on ship hull. The first completed software application was developed at the Leningrad Shipbuilding Institute in the early 1980s and entitled iSCalc. And for more than 2 decades, it was extensively used to perform appropriate calculations. So the next important step was the development of multifunctional software solution, which was developed by direct participation of authors at the Ship Structure Department of State Marine Technical University on order of Research Department of the Bureau Veritas. And then the separate fragments of iStar source code were converted into an independent computer programs. And the last version of the program is the program released in 2019, and it constitutes a highly upgraded and consequently more mature version of previous version in respect of functional capability, structural configuration, input and output data arrangement, computational tool set. At that, it should be mentioned that other software products developed, for example, at the Krylov Shipbuilding Research Institute, the different programs intended to solve the different tasks of ice load determination. The software developed at the Central Marine and Design and Research Institute and at the company Polytechnic. So in the next part of my presentation, I would pay your attention on the functional capabilities of the last outer software for direct calculation of ice loads on ship hull. So I will highlight only the main capabilities. So to determine the local ice loads on ship hull under dynamic interaction, we used the model for side impact against the age of motionless ice cover during the translational ship motion. It's the well-known model proposed by Popov. So here you can see the set of local parameters being determined. To determine the global ice loads, we use the model for stem post impact against the age of motionless ice cover during ship ramming. So to set the contact pressure, there I used three models for for internal mechanics. There are the traditional hydrodynamic model, modified hydrodynamic model, and a new advanced model for dynamic ice failure under local crushing. So to determine the local ice loads under static interaction, it means under ship nipping in ice, we used four different models for failure of ice cover, owing to the flexure, owing to the constrained rotation, owing to the buckling, and owing to the plastic deformation. Within this software, we can, for example, select the different scenarios of dynamic interaction. It means the different types of impacts. To vary the water area, the season of ship navigation, the trajectory of ship motion, the direction of ship motion in ice. For example, we could account or no account the friction, to vary the pickedness for distribution of pressures. So we could change at the initial stage, the morphological type of ice cover, the type of crystalline structure of sea ice, the geometric form of ice edge, and different approaches to the determination, mass characteristics, physical characteristics of sea ice, strength characteristics, and elastic characteristics. It could be the manual input or calculation depending on different recommendations given in the well-known sources. So, and then I will show some results, visualized results of direct calculation of design ice loads. The diesel electric icebreaker Vladivostok was under consideration in this study. This ship was built at the Vyborg shipyard and commissioned 6 years ago. This ship is intended to perform the icebreaking operations in the Baltic Sea in the winter, spring, and in the Arctic seas in the summer, autumn. Here you can see the main dimensions of this ship. So on this screen, you can see the local, distribution of local ice loads on ship hull under dynamic interaction with the ice cover. So the different parameters of ice load represented by geometric, it means depth of ship side penetration, height of contact zone, length of contact zone, and force parameters such as ice load intensity, linear ice load, and total contact force. The distribution is along the length of area of four-body entrance because we have considered the ahead rectilinear ship motion. So then the distribution of global ice loads on ship hull under dynamic interaction with the ice cover. So here we can see on the left picture, we can see the distribution of vertical shearing force, and on the right picture, you can see the distribution of vertical bending moment along the length of entire ship hull. Under different speed of ship motion in ice, and the distribution of local ice loads under static interaction with the ice cover. It means under nipping in the motionless ice field in the winter, spring navigation period. Also the 6 type of parameters, 3 geometric parameters, depth of side penetration, height of and length of contact zone, and 3 force parameters, force of components such as ice load intensity, linear ice load, and total contact force. The distribution is along the length of entire ship hull. And in conclusion, I would to say that the comprehensive application of direct calculation methods to assess and to forecast the external environmental effects of any nature, including the ice loads on different marine infrastructure facilities. It means not only the ships, but also the platforms, conforms to the contemporary worldwide trends to the full extent, and therefore the comprehensive introduction into the real process of designing the ice strength and hull structures of ship hull appears to be reasonable and demanded. But in this case, we should understand that it is necessary to have the availability specialized software and very verified and theoretically substantiated methods to realize these procedures. Thank you for your attention.
Thank you very much. Again, I'm asking for comments to be written to the chat in the YouTube channel, but then those who are on the Zoom room can ask questions directly if there are any. I can then start if there's any else. How does your method relate with the regulations? I mean, as you said, that there's of course the kind of the ice class rules. So how does your direct method compare with the ice loads one obtains from the regulations?
So we regarded three sources of information. First source there where it was the normative values of ice load. The second source was the results from the full-scale trials of this ship, and the third source was the results of our deterministic direct calculation. Here I could not show the results of trials because it is the commercial property, but I could say that the difference for particular mode of ship motion, it means the rectilinear ahead motion in ice field in the winter navigation period. We regard this scenario of interaction is the difference is no more than 20%. 20%.
Very good, very good.
But the internal parameters of the direct calculation model could ask to improve and to upgrade the results and to put them in correspondence with the full-scale measurements, with the results of full-scale measurements.
Any other comments? Then I have another comment, which is more like a personal view, I would say. I was surprised to see that you still refer to Kurdyumova-Kaysin hydrodynamic ice load model, because I mean it's not. It was a very good model when it was introduced, but for a number of decades, experiments have shown that the physics is not correct in that kind of hydrodynamic model. So I was kind of surprised that you keep that kind of legacy model in your system.
In any case, we should understand that the regulatory calculation, it's a normalized adapted version of the direct calculation. And for example, the currently valid requirements of the ISRS rules are based on this approved method of direct calculation. So the correspondence between the results of regulatory and direct calculation is close, yes, are close.
Okay, thank you very much. I don't have anything to add here. Thank you. Nice presentation. Maybe you can stop sharing, okay. And then I can ask Brandon Nickerson to try sharing your screen so that we can make sure that everything is up and running.
Sure, I will try soon. Here we go.
Here we go.
Can you see my presentation?
We definitely do.
Sorry?
We do, yes.
Oh, perfect.
Everything is fine, yes. And also we can hear your voice.
Thanks very much. Can I go ahead then?
Let's wait 2 minutes so that if somebody joins this room from another room to hear your talk, so we don't start in ahead of time.
Sure, no problem.
I think we are close enough to 1 o'clock now. So Brendan, please go ahead.
Thanks very much, Ika, and thanks to all the previous presenters. My name is Brendan Nickerson, and I'm coming to you live from Stellenbosch University in South Africa, part of the Sound Vibration Research Group here. And I'm presenting a bit of our research on a inverse model that we've developed for the estimation of axial propeller loads. So just a little bit of a background to start. We're interested in finding out the loads in the propeller, because if you have significant damage to a propeller while you're traveling through ice, your ship is obviously in a very dangerous position. So this research forms part of a broader attempt to understand our propeller loading, but through measurements on the propulsion shaft. And the reason for this is due to the difficulty in measuring the propeller loads directly, specifically due to the harsh operating condition that the propellers operate in. So your sensors are very likely to get damaged. Also, our research up until this point is mainly focused on the torsional loads, so the ice-induced moments. And we've now attempted to adapt these models to investigate the axial loads. All right, our research uses the SA Gullis II polar supply and research vessel as a case study. And we've been conducting full-scale measurements on the ship since 2012, usually during the resupply voyages for the South African and Arctic base. The ship was in dry dock during March in 2017 for routine maintenance operations. And this gave us the opportunity to conduct measurements on the blades directly, which we don't normally have access to while it's underwater, as well as conducting measurements on the shafts. And what we attempted to do with these measurements was to investigate the frequency response of the propulsion shaft system. So what we did here was we installed accelerometers at a few locations along the shaft, as well as on the blade. And we excited the blade, both the propeller blade and the hub, using a sledgehammer. Unfortunately, we couldn't get a modal sledgehammer, so we struggled to measure our actual impact forces. But we could still excite the structure and attempt to capture a frequency response. So this frequency picture that you see over here, sorry, let me just create a pointer quickly. There's a number of frequencies that are highlighted over here. The most important ones here are just these solid black lines, which are the actual design frequencies for the system, based on designs by Rolls-Royce. And the dashed back lines are frequencies that we identified both on the blades and on the shaft that are very close to these design frequencies. There's also a number of additional frequencies, both on the blade and the shaft. Some of them are indicated by these blue and red lines, and those are likely due to local resonances on the system. Okay, so the idea then was to use that frequency data to compare to our inverse model to attempt to see if it was representing our shaft correctly. So the inverse model itself was developed using a differential element of the shaft, which you can see over here. And simply by summing the forces along that element, we were able to develop our partial differential equation of motion for that shaft. The loads then applied to the shaft include the unknown propeller thrust, which would include any ice-induced effects, as well as the known loads, which is the inertia of the propeller, the mass itself, as well as the mass of any entrained water, the hydrodynamic damping that's applied to the propeller, and then on the other side of the shaft, the thrust bearing that is there to catch any thrust loads and protect the motor with its own stiffness value. All those loads are then included with the partial differential equation of motion, and we then apply modal superposition in order to alter that partial differential equation into a set of ordinary differential equations. So I apologize for the horribly long equations that are now on your screen, but the idea is that once we've applied that modal superposition, we end up with a set of equations, one of which is for our rigid body mode for the shaft, and the remainder of which are for our flexible modes. And in each of these equations of motion, we will have some other inertial term, as well as a damping term and our stiffness term. And then again, our unknown axial propeller load that we are attempting to solve for. The only problem there is that we only have n equations, so one for each mode that we use in our modal superposition. And we have the additional unknown, which is the propeller thrust load. So we need to introduce one more equation in order to solve the system. And from that, we would get that by conducting a measurement, a full-scale measurement on the shaft itself, and relating that to our modal coordinates. And then we have our n+1 equations representing our n modal coordinates and our additional unknown thrust load. And then we are able to solve the inverse problem. Okay, so we then compare that inverse model to our frequency results that we got from the dry dock measurements. And we considered 3 different variations of the model to investigate what the different effects are of including these variations. And the first variation we looked at was to consider the thrust bearing as simply a fixed support. So there was no stiffness there. And that also eliminates the rigid body mode. Our second condition is as presented. So we have the spring boundary condition at the thrust bearing using the spring stiffness, or using the bearing stiffness from the manufacturer. And our third variation, we also included additional masses. So the bearings that are attached to the shaft, the coupling of the shaft, all the additional masses that are present on the shaft we included in the calculation. And then we accounted for those similar to the way we counted for the propeller mass. And in this case, what we found was that contrary to our torsional model, our axial model became a lot more accurate with the more additions we considered. So for example, without considering the spring and the mass, the spring support of the thrust bearing and the masses, our frequencies were quite far off of the design and measured frequencies from the dry dock. And then as soon as we considered the thrust bearing as a spring support, we got a much better agreement between our frequencies, between our design and our measured frequencies. And again, once we started including the additional masses, we got an even better agreement. You can see that by the time we've included all the masses in the springs, we're already down to about a 3% error off of our first natural frequency. Yeah, so based on these, as I said there, the model becomes a bit more accurate as we include more of these additions. And the idea is now that we can use this model to attempt to estimate inverse propeller loads from full-scale measurements. From the full-scale measurements, we should confirm that the first mode is dominant, since the model is already accurate enough in that region, and we should then be able to use the model to do these estimations. We also can consider future improvements to the model, accounting for varying cross-sectional area, which the model doesn't account for at the moment, and the particular shaft that we have modeled does have a varying cross-sectional area. So accounting for that will account for additional mass, which we've already seen does increase the accuracy of the model. And we could also include any additional damping or stiffness, for example, due to bearing lubrication. Thank you very much.
Thank you very much. Very nice. Very, very nice. This last one is very nice photo. Or I don't know if it's a photo, but anyway.
It's a scan we actually took during the dry dock that
Yeah. Any questions from the audience? Then I ask a simple question. In a most positive case, I mean, what can you deduct with this inverse method? Total load on a blade or more? Or it's just a mean load on the propeller blade? Because I mean, you're really measuring something from the axis, and you can have, what I'm thinking, I say first what I'm thinking, then you can tell me if I'm wrong, because when you're measuring something from the axis, there can be many different ways of creating that reaction from the blade side.
Yes, so the result that we get from this inverse model would be the total load acting on the propeller. So it's not the different loads aren't separated. It will account for everything. Effectively, what we measure on the shaft, we'd measure, for example, we'd measure the response due to an ice impact. We'd measure the load due to the ship moving, the hydrodynamic damping, all of those loads would be measured. So the inverse estimation that we get would include all of those loads as well.
Yeah. Yes. Very good, very good. Those were we're a little bit ahead of our time. Not much. I can't see any questions in the chat, so I can only thank all the authors, presenters of the 4 papers. We covered different aspects of ice loads and structures. Thank you very much. 4 nice talks, and I think it's now time for lunch, unless there is something. How about the administration? Do you want to say something? No. The next thing in the program is lunch, which then will be over by 2:20. I close this session. We're a little bit ahead of time, but I will close this session as I don't see any questions. Thank you, everybody, and have a nice day.
Thank you.
Thank you very much, Ika.
Thank you.
Thank you.
Good morning or afternoon, everyone, whatever time you have.
Good afternoon. The most time is 15:14, so we have about 5 minutes before the start of the section. The participants, if they want, may check if they have the ability to run their presentation.
Sure. Maybe we can start based on the program. So I believe the first one is Sangrok. Sangrok, do you want to run your presentation yourself?
Yes, I want to run my presentation myself.
Will you be able to share it? We can check all whether you'll be able to share the screen. Do you have?
Is it working?
Yes, perfect. Okay, so could you stop sharing and we can check orders before we run? It's a little of delay. Yeah, or we can keep it. It seems to be working. Okay, so maybe could you stop sharing the screen, please? If possible, excellent. And the next one would be, oh my gosh, where is my program? It's Yunji Samamura. Are you planning to share your presentation to play it yourself, or? Will you be able to share it? Excellent. Yes. Yeah. Perfect. Works well. Okay. So maybe if you could stop and share it. Excellent. And the next one on the program will be Fang Li. Fang.
Hello. Yeah, it's. I will try my screen sharing.
Yeah.
I have shared my screen.
Yes, works. And will you be able to?
I will play. Yeah, do you see it in full screen?
Yes, and can you advance the slides?
Yes.
Perfect, works well. Okay, so could you stop sharing, please? And
pause share. Stop share.
Okay, excellent. And the next one is Taiki. He had to re-enter because he could not hear. So Zongyu, would you please check whether you can share the screen? You are on mute, so I don't hear if you are saying something, but...
Hello, I was changing my name. Sorry.
Okay, good. So if you could please try whether you can share the screen and play the presentation.
Sure.
Excellent. And if you could try to do the presentation mode.
Yeah.
Good. And will you be able to advance? Could you change the slide? Okay, that's fine. And Taiko, now, can you hear us? And would you please try to share the screen to see whether it's working? I cannot hear you. You seem unmute, but I cannot hear you. Okay, I'll... if it doesn't work, if you have issues, I don't know whether the assistant could try to help. And eventually, I do have your presentation. I could play it, but I will not be able to provide any comments. No problem. It's technology. So I don't know whether it would help if you did restart your computer while we are in the session. No. And now you are on mute. You are on mute, Taiki, now. No, you are not. Okay, no, we cannot hear. Unfortunately, we cannot hear.
Well, we had such an experience when we had presentation without speaker because busy. But if the presentation allows, we can maybe show it without sound if the presentation is rather informative. It's better than nothing.
Okay, perfect. So what we'll do, maybe because we are at the beginning of our session, so maybe we'll start. And Taiki, if you cannot make your sound work, you can either play the presentation only, and it will allow us to allows us to read it, or I can play it for you because I do have it, and I could eventually share the screen. And yes, so that being said, it's my pleasure to welcome you all to the session Ice Loads on Vessels 2. I'll be convener of this session, and I would like to introduce our first speaker, Sungrok Cho, who will be presenting the estimation of local ice load on the IBRV Aron using enhanced influence coefficient matrices. So please, Sungrok, share the screen and go ahead with your presentation. Thank you.
Okay, is it working?
Yes.
Okay.
Perfect.
Okay. Good afternoon. This is Songnok Jo from Korea Maritime and Ocean University. Today I'll talk about enhanced influence coefficient metrics for estimation of local ice loads on IBRV Aron. The presentation will be carried out in the order of 4 chapters as follows. The first chapter is the background. The practical approach to estimate the local ice load on a vessel during icebreaking process is to measure directly at the contact location with the sea ice. However, as we know, it's very difficult because there are no proper measuring sensors to withstand the ice load on the outside panel of the ship's hull. Therefore, by installing strain measuring sensors inside the hull plate, it's possible to indirectly measure the strain due to sea ice interaction. And then the measured strain can be converted to load using the method of the influence coefficient matrix, ICM. And the ICM is frequently adopted to obtain a relationship between the hull stresses and the local ice load. And the ICM representing the relationship between the input forces and the resulting responses of a given structure system. So far, in estimation of localized loads, the ICM uses a relationship between the hull stresses and ice pressure acting normal to hull structures, as shown in this figure. And in here, the von Mises equivalent stress are usually used as the response of the hull structure. And however, this sometimes misleads the actual Hall responses because the direction of the calculated von Mises stress are not necessarily consistent with the ice loads on the ship's hull. So to overcome this inconsistency, instead of von Mises equivalent stresses, hull stress for all in-plane directions can be used. And this is what we did in this study. 3 in-plane stress components, including shear stress from fiber optic sensors and the rosette type strain gauge installed inside the ship's hull, are utilized to derive the ice flows in 3 directions as shown in this figure. And an enhanced influence coefficient matrix can be assembled to give the actual hull responses. And then we use the enhanced ICM for analyzing to retrieve the patterns and the magnitude of localized load from the 2019 Atlantic voyage. The method of ICM derivation relating localized pressure to hull stresses via von Mises equivalent stress, as shown in this equation. In here, the C is the influence coefficient matrix, and P is the ice pressure normal to hull plate, and sigma is the von Mises equivalent stress calculated from strain gauge measurement. And this is most frequently used algorithm in estimation of ice load on ship's hull. However, von Mises equivalent stress does not represent the actual stress component. Besides, it always produces positive values, and it cannot be used on index to indicate the direction of stresses. So Sung and Zhang derived an ICM using 2 stresses in the X and Y direction, respectively, instead of using von Mises equivalent stress as shown in this equation. Meanwhile, these 2 methods calculate ICM based on ice pressure acting normal to the hull plate. But in the actual field condition, the direction of ice load acting on hull plate varies depending on the location and interaction processes between the hull shape and ice features. Therefore, for more accurate estimation, it may be more appropriate to consider any possible ice loading direction at the contact point. So in this study, for the derivation of enhanced ICM, we use the 3-axis forces represented by X, Y, and Z, and the 3 in-plane stress expressed by sigma X, sigma Y, and tau XY. And enhanced ICM is presented as shown in this equation. Now we move on evaluation of ICM for Around's hull plate. In December 2019, the Korean icebreaking research vessel Around conducted an ice field test in the Ross Sea, Antarctica. And during this field test, extensive amount of strain data was recorded from strain gauges, also fiber optic sensors installed on the inside hull plate as shown in this figure. And furthermore, various information such as ship speed, ice thickness, etc. were also collected from integrated monitoring system. And let's take a close look at the sensor installation location. In port side, the 13 rosette strain gauges and fiber optic sensors are installed. And in starboard side, the 12 rosette strain gauges and fiber optic sensors are installed. And as you can see in this figure, the distance each sensor is 800 millimeter horizontally and 500 millimeter vertically. So based on the distance between the sensors, it was assumed that the area represented by one sensor was 0.4 square meter. In order to perform FEM for ICM derivation, the bow of Around was modeled as shown in this figure. At this time, the transverse bulkhead in the stern direction constrained 6 DOF, and we gave a symmetry condition at the center line of the hull. And we defined x-axis is for the longitudinal direction, y-axis for lateral direction, and z-axis is for vertical direction. The ice field strain data recorded during the IBRV Around's 2019 Antarctic voyage is analyzed to retrieve the patterns and the magnitude of localized load using the enhanced ICM in this chapter. And this video shows the typical ice condition during the Around's 2019 Antarctic voyage in the south of Ross Sea. And during the voyage, the various ice conditions were encountered, such as peg ice, ridge, including level ice condition, as shown in this video. And among the data measured under various ice conditions in this paper, an 8 minutes data set measured under peg ice conditions was selected and analyzed, and only the port side data is considered. As shown in this figure, the strain data is measured in here, and ship speed is measured using a GPS installed outside the hull structure near the center line of the ship. And information for sea ice thickness is obtained using image processing software and the video images of the broken ice pieces recorded from the center line of the ship. And this figure shows the image processing software for estimation ice thickness. And as you can see, this software estimates the ice thickness from ice sheet cross section. The ice sheet thickness using the software is observed to be 0.5 to 1.8 meters, but our cross-section of the broken ice sheets are not recorded. So therefore, our thickness data is not known in this data set. If the hull plate is assumed to be a two-dimensional elastic plane, the measured strain data from each sensor can be converted to in-plane strain using these equations. And then in-plane stresses can be calculated from in-plane strain using this equation. And using the calculate in-plane stresses and the inverse of the influence coefficient matrix, the load applied to the measuring area can be estimated like this equation. The ice load components in 3 directions estimated using the enhanced ICM is shown in this figure. And you can see the largest force occurs in X direction. Meanwhile, similar loads occur in Y and Z direction, but you can see that the Y direction has a larger load. And in here, we can see the load acting on the measuring area is not only in the normal direction. Using 3-axis forces, we can calculate the force in any direction, such as normal or tangential. And in this study, we calculate the normal force acting on the measuring area. And assuming a flat plate and a unit normal vector, the ice load Fn normal to the plate can be calculated. And this figure shows the Fn against time. And in here, the peak ice load loss of 0.4 meganewton or higher are classified as events. And the total number of events in this data set is 1,152. And the event is shown in this figure with ship speed as a horizontal axis. And it's found that the maximum peak ice load is 3.37 meganewton with the ship speed 7.35 meter per sec at that instance. And if we dividing the maximum peak ice load by the measurement area, 4.8 square meter, the maximum peak ice pressure is 0.702 megapascal. In the conclusion, to sum up our study, a new approach to calculate the influence coefficient matrix is presented, and the ice field strain gauge data recorded during the IBRV allowance 2019 Antarctic voyage is analyzed. The components of local ice load can be estimated with the use of enhanced ICM. The new approach captures all the important patterns of the ice load in time series, and the magnitude of local ice load can be obtained in a reasonable range using the new approach. And the ice load in the vertical direction FC may be connected to bow impact or beaching process. And also the load in the longitudinal direction FX may be used for the determination of ice resistance if we can measure data for the entire hull. And this research was supported, funded by CRISO, and the collaboration with COPRI for onboard measurement of the Araon are greatly acknowledged. And thank you for attention.
Thank you very much. Very interesting presentation. Do we have any questions? Anyone from the Zoom room? Or I don't think there are any questions on YouTube. So anyone from the Zoom room, do you have questions? If not, I have one question. Did you also do any measurements in compressive ice, in pressured ice conditions, in severe ice conditions, or was it more the conditions in level ice, slightly ridged maybe?
Yes, we measure the strain data under the level ice condition, and we analyze the data under the level ice condition, but in this presentation, we only use the strain data from the peg ice condition.
Okay, there is a question from YouTube. I'll read it. To obtain the ice pressure values, you need to set the contact zone form and the pressure distribution law. What were these parameters accepted in your study? Or did you reproduce only the total interaction force?
Actually, we decide the contact zone from the location of the installation, the sensor, like as shown in this figure. And we didn't use the parameter. We didn't use the parameter for decide to the contact zone. So we just use the location of installation sensor.
Okay. I guess there are no further. Oh, one more question. Did you check how sensitive your measurements are if the contact area changes from the assumed area, the area you apply your FEM?
Sorry, I can't hear. Can you
Okay.
say that again?
Did you check how sensitive your measurements are if the contact area changes from the assumed area or from the area to which you apply INFEN?
Yes, we check the sensitive if the measurement area change, and if the sensor, if the installation sensor, if we install more sensor on same measurement area, and the good results can derive from that more sensors. And if we install the few sensors at same measurement area, and is the bad results derived from the bad result will derive.
Okay, so thank you very much for your presentation. Interesting, and I'll ask the second speaker. I'll introduce the second speaker, and in the meanwhile, if you could stop sharing the screen and the second speaker start sharing the screen, that would be great. So our second presentation will be presented by Juni Sawamura. The presentation is titled Numerical Simulation of Ship Ramming in Very Thick Ice. And if you could please introduce yourself, just in case I mispronounce your name. Thank you very much.
Thank you for Chairman. So my name is Junji Samurad from the Osaka University, Japan. And today's topic is numerical simulation to predict the ice breaking distance to observe ship ramming in the very thick ice condition. And then, so as you already well known, so we have two kinds of ice breaking mode. So first one is continuous ice breaking, in which ice breaker can break the plate ice continuously. And in this case, the ice thickness is 1 or 2 meters, so not so heavy ice condition. And then, so if so icebreaker encounters a very heavy ice condition, so we use ramming, charging the ice breaking mode, in which breaking mode icebreaker at first accelerate her speed and then collide with ice edge, and then sliding up onto the plate ice, and then break the plate ice by gravitational energy of the icebreaker. And then this case, icebreaker cannot break the plate ice continuously. Then she go back to the starting point here, and then again she accelerates the speed and then collide with plate ice and then break the ice. So during the ramming ice breaking operation, the icebreaker continue this kind of breaking process. And then this picture shows the Japanese Antarctic research icebreaker Shiratsu II. And so we quite often encounter the very thick ice conditions when we go to the Japanese Antarctic research station. And then, so and the bottom picture shows the running operation of the Japanese research icebreaker. And so we are always struggling to go through this kind of the very thick ice condition. So it's very important to predict the ice breaking distance of the ramming operation for safe and efficient operation. So this paper proposed a two-dimensional model to calculate the ice breaking during ship ramming in extremely thick ice condition. And then the calculation results are compared with measured data. So when an icebreaker encounter submerged ice, this is the purpose of this paper. And then at first, I would like to explain the measured data. I onboard the Japanese icebreaker Shirase in 2030, and then so I measured data such as ice thickness and also ship motion. And then this mapped its ship route from the Tokyo, Japan to our research station, Antarctic Research Station. So Japan is here. And then so our research station is here. And then this map is close up mapped near the our research station here. And in 2030, so we also have had encountered quite heavy ice condition. And the March-year ice started from here, and the Japanese research station here. And then so almost this area is March-year ice. And then so I used measured data in this green area, and then this area, the ice thickness, average ice thickness is 3.78 meters. So then it's a little bit quite heavy ice condition. And here there's a measured data. So upper figure is ice thickness and ice breaking distance, measured ice breaking distance. Red one is ice thickness. And ice thickness starting point of the ice thickness is 5 meters, and then gradually decreasing until around 2 meters. And then black one is breaking distance of each running operation. And at first we just only under 10 meters, and then gradually increasing ice breaking distance. And then finally, so we got over the 100 meter ice breaking distance. And the bottom one is a ship motion. So black one is ship speed, and the red one is pitching motion, and then blue one is rolling motion. At first, icebreaker accelerates the speed, and then collision with icebreaker occurred at this around this point, and then rapidly increasing, decreasing ship speed decreasing. On the other hand, pitching motion is rapidly decreasing. So this was this is a typical time history of the ship motion of the running operation. And next one, so I would like to explain numerical modeling, my numerical modeling. So when we make the numerical modeling of the ship running, so we have to describe, represent the three phenomena. So first one is a ship ice collision, and second one is ship sliding motion, and also ice breaking of the plate ice. And also we have to describe the ship ice flows interaction after plate ice failure. And then so calculation of the collision point can be obtained by circle contact detection techniques, which is used in computer graphics techniques. And so we consider the two kinds of the forces as the ship ice contact force. The first one is contact force, and the second one is friction force, as described this equation. So contact force is proportionally increasing the ice pressure area and ice pressure forces. ice pressure. And in this paper, so I use the contact value and then ice pressure, and the ice pressure is and then so compressive strength of the ice is used for the ice pressure. And the friction force is Coulomb types of the friction. And finally, so we got total ice force and describe these equations. Fz is the vertical force is here, and then horizontal force is here. And then so for the ice breaking, so I assume the bending failure. And bending failure of plate ice occurred when the contact force, the Fz vertical force at the crushing surface increases as the ship advances and exceeds the bearing force of the plate ice, and then so plate ice is broken. And the bearing force is, can be obtained in this equation, so proposed by the Castellian. So he assumed the same infinite elastic fine plate as shown in this figure. And then so length of the broken ice flows can be obtained in this equation, which one obtained from the two-dimensional semi-infinite elastic found in beam. So just I use a beam theory, a statics beam theory. And then so ship motion and ice flows motion and ship ice collision, I use a physically based modeling, and the ships and ice flows are assumed to be rigid bodied, and the ship's motion and ice flows are described using 3 degrees of freedom rigid body equation. And then collision response is assumed to be instantaneous impulse forces as describes this equation. And fluid force just use this simple equation. Yeah, drag force are assumed. And here is a calculation condition. So numerical result was a proposed method compared with the ships running the data collected when Japanese icebreaker encountered the Malaysia ice during the Antarctic voyage in 2040. And this one is principal dimension of the Japanese icebreaker Shirase. Length is 126 meters, and the maximum breadth is 28 meters, and draft is roughly 9 meters. And the mechanical properties are shown in this table. And here there's a calculated ship ramming. In this case, the ice thickness is 4.5 meters, and input thrust I give the constant thrust power, and in this case, the 40 kilonewton per meter, and the initial speed gives 5.0 meters per second, and in this case, the ice breaking distance obtained 22.84 meters. And ships go to the initial speed of 5.3 meters, and then so collide with ice edge, and then crushing occurred in this area. And in that case, after colliding with the ice edge and immediately broken by the bending failure here, and then still so ships have powered and then sliding up to the plate ice. And then in that case, in this case, icebreaker cannot break the plate ice, so then sliding down the ship sliding down on the plate ice. So this is a running process. And here there is a calculated time history of the ship motion. So black one is ship speed, and red one is pitching motion. So starting speed is 5 meters per second, and the first collision occurred at this point. And then ship speed is gradually decreasing. On the other hand, ship pitching the motion is increasing. And then here, so finally, so ships sliding down to the plate ice. And here, bottom one is time history of the breaking the force. Ice force. So contact here, and then immediately quickly increasing the ice force, and the ice breaking occurred at this point, and dropped it immediately dropped ice force dropping, and the second contact occurred at here, and then so contact force increasing, but in this case the ice force does not increase for breaking the plate ice, and then so just we can see the interaction forces here. So this is a time history, and finally, so I want to show the comparison of the measurement data and calculation. So we carried out 5 cases. I sequenced 3, 3.5, and 4, 4.5, and 5.2 meter. And then so in the 3.0 sequence cases, so we carried out 3 consecutive running calculation and then penetration obtained here. And the red one is the average ice breaking distance, and the blue one is pitching motion. Yes, and the 5.0 meter case, we carried out 8 consecutive running calculation, and we got the penetration distance here and the average here. And then so in the 3.0 meter ice thickness, so we got the penetration distance around 6 meter, and then 3.5 is around 40 meter. And then in the measurement ice thickness 3.25, so breaking distance around 40. And then so then roughly can obtain, so we can show the good agreement, the calculation and the measurement. And then 5.0 meter ice thickness cases, also penetration distance 5, and then for measurement 4.373 meter. So breaking the distance 10 meters. So then also we got the good agreement in the for the penetration distance, but the pitching motion here. So 3.0 on only 1.8 pitching motion, and the measurement also 1.57. And then so in the calculation, the pitching motion in the 5.0 meter, so 4.250, but the measurement is only 2.60. So then pitching motion of the calculation become quite larger than measured data. So this is our calculation result. And the conclusion, so this paper proposed a 2-dimensional model to simulate ship ramming. And the calculated penetration distance and the pitching angle are compared with measured data. And the calculated penetration distance agree well with measured one. However, the calculation produced a large pitching angle than the measurement. The numerical model does not consider the flexure. So reason is the numerical model does not consider the flexure deformation of the ship and the plate ice, and also effect of the snow and ice melting the water from the ice surface. And also mechanical properties of sea ice is quite important for the calculation. So then, so these effects should be included in calculation with the future work. So this is acknowledgement. Thank you for everyone. So that's all. Thank you for listening my presentation.
Thank you very much for your presentation. I have one question from from YouTube. In your case of extremely thick ice, which is ice thicker than 3 meters, was it possible to collapse ice owing to the bending? Is not the factor 0.518 in Formula 1 for bearing force too small?
I don't know how to break the ice for quite thick, heavy ice condition. But this case, I assumed so ice breaking occurred at the bending mode. So then so I compared with measured data, and then so we got roughly good agreement. So then so it's very difficult to answer the question. So okay, yeah, no.
Okay, that's all. I don't think we have more questions on YouTube. Anyone in the Zoom room, do you have any questions? Okay, if not, I'll introduce our third speaker. And again, if you could please switch the presentation, stop sharing and start sharing, that would be great. And feel free to use the cameras. So for the third presenter, the presentation will be given by Fang Li, and the title of the presentation is Full-Scale Measurement of Ship Performance and Ice Loads in Antarctic Ice Flow Fields. So let me welcome the next presenter, next speaker, and go ahead.
Thank you, Ivana, and dear audience in front of the screens. My name is Fang Li. I'm from Aalto University. Today I'm going to present some full-scale measurement result of the Antarctic, the ship in Antarctic flow ice fields. So the data we got from this Agulhas in the Antarctic voyage, it starts from 2012, from when it starts the annual voyage to the Antarctic for the supply and research task. Now, up to now, it has been traveling to there for 9 years. During this 2018 and 19 voyage, the ship has been extensively gone into flow ice fields. So we decided to have a look at those data and then publish for others to use. So during this voyage, the ship starts from Cape Town in South Africa, and then it heads south to Antarctic continent. Then after that, it heads to the west to Weddell Sea, and finally came back to Cape Town after about 100 days. And the measurement includes ice condition monitoring, the ship performance and ice loads. So for the ice condition, there are two main sources of measuring. The first one is visual observation, which is the traditional way of measuring the ice condition parameters like thickness, concentration, and flow size. The thickness was measured by comparing the turned flow with the measurement stick. Then the concentration, the flow size are basically a kind of visual estimation based on what is seen from the bridge. And then in addition to that, we have installed an ice condition camera. The idea is to take ice photos every 2 seconds. Then we have a large number of photos showing what kind of ice is in front of the ship. Then we process the photos with a machine vision algorithm, which I will show in the later part of the presentation. The measurement of ship performance includes the power, the propeller settings, speed, and rudder angle. So basically, we know how the ship was maneuvered throughout the voyage. And the navigation data includes the course over ground, the heading, and also the location of the ship. And then the ice load includes the measurement from shear strain gauges installed at the 3 locations of the ship, including the bow shoulder, and the stern. The data we get on the bow shoulder had some problems, so we mainly focus on the data we get at the bow and at the stern. And in addition to that, as you can see from this picture, we also have installed some inertia measurement unit, like here, for example, and here. So we get an idea of the ship motion in water and in ice. And the aim of this paper is to firstly select some segments of data in Antarctic floe ice fields so that we can publish the data in open access. The selection of data aims to cover a wide range of thickness, concentration, and flow size, so we get different ice conditions. In total, we selected 10 segments. And then the second aim is to, after that, to provide a general view of the selected segments. For example, the resistance, the ice loads that we measured. And then the third one is that we want to address the potential of the data, especially related to the machine vision processed data, which I will present later on. So in total, we have the 10 selected cases, and the main information of these 10 cases are summarized in this table. So you can see from these figures on the right-hand side that clearly the concentration varies from very small to very high. And then the flow size also varies. We have categorized basically into 4 concentration, like 30%, 50%, 70%, then 90%. The selection criteria includes that we want small variation of ship speed, no major change of ship course, so the ship wasn't intended to turn to another direction, and then no obvious drifting of ice flows. But of course, the ship was maneuvered by the crew all the time, so nothing will be constant. And here is an example of a video that the ship was going in 50% coverage ice flow field. As you can see, there are of course small maneuvering that the ship swing in through the ice field. There are some ice flow. You can see there are some ridges, the natural result of deformation. So, and then here is the the ice load signal, which was measured on the bow during this half an hour. There is a half an hour navigation period. Then the resistance was estimated by estimation of the net thrust, and then deducing the inertia times the mass from the net thrust. And here on the colorful picture, you can see the summarized the calculated resistance as case-wise. So the largest resistance are from the highest concentration, which are case 8 to 10. And then after that, the higher thickness is in case 4 and 5 also leads to quite large resistance, although the concentration is only 50% in these two cases. And also the effect of speed is also visible from this comparison between the case 1 and 2, which has a higher speed, and then case 6 and 7, which has a lower speed but higher concentration. And the resistance in these 4 cases are quite similar. We don't see a clear influence from flow size because naturally the volume of the ice is determined by the concentration and the thickness. So flow size may have some effect, but not as dominant as the other factors. Then the second thing we look into is the frequency of ice loading on the hull of the vessel. For this, we extract the ice load peaks via Rayleigh separation, as you can see from the picture below. And then we get the load peaks and we summarize the load peak per distance, so which is per kilometer in the figure on the right top. It's a bit hidden by the video, but you can see that most of the load comes from the case with higher concentration. So the concentration 90% cases have more than double of the load frequency than all the other cases. And then on this one in the middle, you can see the load frequency at the stern. At the stern, a similar thing is shown that the concentration has a major influence on the load frequency, but there's a quite a large variation between case 8 to 10. And the reason we found is that from case 8 to 10, the ship was frequently, the frequency of maneuvering of the ship is rather different. So we extract the rudder angle peaks from the rudder maneuvering history and summarize in the histogram here. And we found that from case 8 to 10, the frequency of loading at the stern has a very high correlation with the maneuvering frequency of the rudder. So which shown that the influence of maneuvering to the load at the stern. Then the next thing is ice load magnitude, because the first thing we see is that the concentration has very little effect on the median, on the load statistics, because it's basically quite similar. across different concentration. Then the largest load at the 90% quantile happens in the case 3, which has case 3, and we look into the reason and we found that in this case the flow size is quite large, and in this case the flow size is quite large, and there are some ridges on the flow which apparently has leads to quite a lot of large ice loads. And then the smallest ice load happens in case 4, which has a very small ice flow, and also case 6, which has very thin ice. So these are a kind of summary of the resistance and the load data depending on the ice condition parameters. And then the next thing is the machine vision results. So the ship has been taking photos of the ice field every 2 seconds, and we use some artificial intelligence technique to process videos. The first thing is to make the author-rectified photos. So we change it from this picture A to picture B, so that it's like what we see from the from the bird view, from the top of the sea. Then the next step we do is to connect all the ice photos within each case, within this case, together to put it into a panorama, which is shown in the right figure. That you can see it's like all the photos are sticked. We stick the photo one on top each other, and all the photos, they have overlap and they have new information from every photo. So finally, we get this whole panorama, which we also know the route of the ship through the field. This is very useful information, because from this we can firstly we can precisely know which flow the ship has been in contact with. And then we can also extract the flow geometrical features from the analysis quite accurately, and we can analyze the statistics, and we can use it for ice flow calculation. For example, what we are doing now currently is that we want to put polygons onto this ice flow, so we can have a fast and easy representation of all the flow geometrical features. And then we can calculate the ice load with for example, the Popov method, and to get the calculated ice loads to validate those calculation methods. And so we see quite a lot of potential which we can get from such kind of panorama analysis. So final slide, a summary. We have selected 10 data segments of the ship in flow ice field. And these will be published in open access, so everyone can use the data to validate, for example, the numerical simulation program, either is for ship performance or ice load estimation. And we expect more outcome to coming from the machine vision analysis. So we get more insights into the ice flow fields and the statistics. So that summarizes my presentation. Thank you for your attention.
Thank you very much. Very interesting presentation as well. Are there any questions either on YouTube or in the Zoom room? If not, I'll have one question. With what you've described, Fang, do you think you'll be able to predict the ice loads in real time using some of the models you've been developing, or combining these with the artificial intelligence and new technologies? So is it the aim? Do you think you'll be able to predict it in real time?
Yeah, I think that's one application, the one potential application of such kind of technology, that we can use the machine vision installed on board the ship to from what is seen from the camera, turn it into extract the information of flow, then get an estimation of the ice loads. So at the real-time assisting tool, the algorithm can perhaps help the captain to make decisions on what kind of route to take through this field. So this can be a kind of a routine assisting tool as a potential application.
Very interesting. Thank you.
Yeah, thank you.
So if there are no other questions, we are perfectly on time. So again, I'll ask you to switch the presentations, including the sharing screen, and I'll introduce our fourth speaker in the session, Taiki Tokudom, and he'll be presenting a paper titled Fluid Force Modeling Affecting on Ice Piece for Ship Navigation in Broken Ice Field. Again, the floor is yours, and please introduce yourself again in case I mispronounced your name. Thank you.
Thank you. My name is Taiki Tokudome. Today, I would like to talk, excuse me.
Perfect.
Today, I'd like to talk about fluid force modeling affecting on ice piece for ship navigation in broken ice fields. This work was a part of Arctic Challenge for Sustainability 2. ARCS 2 is a national flagship project for Arctic research from 2020. We promote advanced and international research on the Arctic and aim to realize the results of the research in society. In this research program, we will aim to construct methods to support shipping operations in the near future in light of environmental changes in the Arctic Ocean. Today's content is related to predicting the performance of ship. A group at Kogakuin University has been developing a ship navigation simulator for situations in which many ice pieces surround the ship hull. To simulate ship navigation in an ice field, it is necessary to address collision and other mutual interaction among ice pieces and the ship. We incorporated physically based modeling into our simulation program. To handle that situation, physically based modeling is a method for solving the motion of rigid body, including collision and friction. Our simulator uses the Open Dynamics engine. we assume that the ice pieces are rigid body that are not mutually adherent. So we ignored freezing effects of ice. Next, we assume that the ice piece is subject to gravity and buoyancy as external forces. The field force on the ice piece is calculated by following equation. For example, there is an ice piece. When ice is broken, if the projection area of each piece is the same, the field force will be doubled. Then the field force model can still be improved. For this study, an added mass model is implemented into the existing field force model to evaluate the field force on ice piece actually. The modified simulator was tested with ship navigation in brush ice channels. Its tendencies were compared with the resistance formula of Finnish-Swedish ice class rule. So we set an added mass for each ice pieces. An object in accelerated motion in a fluid has an additional fluid resistance proportional to its acceleration, which is given the form of mass times acceleration. This mass is called added mass. In this way, conditions close to those of the real sea area are represented. This page explains the added mass factor. The added mass factor of a sphere is 0.5. So we assume that the added mass factor in the x and y direction are 0.5 each. The added mass factor in the z direction was assumed to be as follows. A. When the total volume of the ice piece is above the water surface, the added mass factor is set to 0. B. When the total volume of ice piece is below the water surface, the added mass factor is set to 0.5. When the ice pieces contact each other or the hull, the motion of the ice pieces reverses. The velocity of the ice piece approaches 0 meters per second. The added mass factor is set to 0. C. When a part of the ice piece is out of water surface, the added mass factor is set to 0 when the movement of the ice piece reverses as in B. Otherwise, it is given by a linear equation according to the ice piece's height. From here, I will talk about two calculation conditions. We use the Japan bulk carrier ship model for our simulation. For these analyses, we assumed Panamax force ship. The main dimensions assume that this value is this. The scale ratio becomes 28.5. The condition of the channel used for the simulation was set assuming ice class IA. The ice piece is a sphere. An actual ice piece of 0.5 meter was assumed. The ice pieces were arranged irregularly in 2 layers. There are more than 420,000 ice pieces. The friction factor between the ice pieces is 1.35, based on earlier work by Kohn et al. The friction factor between the ice piece and the shape is 0.1, based on the FSICR guideline. The dimension of the brush ice channel are shown here. The channel thickness is 1.0 meter to conform FSICR guideline. The porosity is 0.28. This is a video we analyzed. The analysis results show no non-physical behavior, such as ice piece jumping or entering the ship hull. Ice piece move along the ship hull. Ice pieces are concentrated around the bow draft line. So I believe that our simulator simulates the motion of the ice well enough. This graph compares the ship resistance between the added mass model and the previous model. We set the ship's direction as positive. So the ship's resistance is measured as negative. The blue line shows an added mass, and the orange line shows the previous model. First, the ship collides with the ice piece. The ship continues to move into the brush ice channel, and resistance increases. The ship resistance reaches its maximum value in about 15 seconds. At this time, the entire ship is in brush ice channel. The average value of resistance for 15 to 40 seconds is the resistance value on the model scale. Added mass is about 17.09 Newton. Previous model is 16.4 Newton. Close to, but a little higher than previous model. This graph shows the resistance value converted to real scale and the resistance value calculated from FSICR resistance formula. I use the cubic law to convert the resistance to actual scale of the ship. The resistance value obtained from the analysis is about 393 kilonewton, while the value obtained from FSICR resistance formula is about 1000 kilonewton. FSI shear resistance formula is more than twice larger. The previous study by Hellman et al. Shows that the resistance value obtained from FSI shear resistance formula is 2 to 3 times larger than the resistance value obtained from the analysis. The present results have a same trend. The effect of added mass is about 4%. In this simulation, the added mass had no large effect. I would like to conclude my talk. For this study, an added mass model is implemented into the existing fluid force model to evaluate the fluid force on ice pieces accurately. Its tendencies were compared with the resistance formula of Finnish Swedish ice class rule. We found the following. Even if added mass model is implemented, the calculation can be done stably. In this simulation, the added mass had no large effect. The resistance value obtained from FSI shear resistance formula is about 2.5 times larger than resistance value obtained from the analysis. That's all. Thank you for listening.
Thank you very much for your presentation. Do we have any questions in like on YouTube or in the Zoom room? If not, I do have like 2 questions. Did you try to test different thickness of brush ice? Did you change the properties of brush ice, such as concentration and the brush ice filling or thickness of brush ice, or you did just the same, use the same conditions?
Condition.
When I ask you a question, I'm a co-author of his paper.
Okay.
I'd like to answer. The answer is no. At this moment, we only tested the normal Finnish Swedish ice class rule conditions. We did another experiment in another study, but we still have not had a good conclusion from that. Is that the answer your question?
Yes, it answered my question, yes. And I have the second question, which is you mentioned about the resistance being larger. Any explanation why? Do you have an idea why, or you are still looking into the explanation?
I don't know, but it is normal for, in our experience, it is normal for the Finnish Swedish ice class rule formula produces larger, or I could say safer result from the compared with the experiment. So I think it is a normal result. We are not sure, but we believe we produces more or less the normal result. And we are not clear why the Finnish Swedish ice class rules rule formula produces larger, rather larger result, but I think that means we believe our simulation is not so bad.
Yeah, no, that's fine. Just question. And there's actually one question on YouTube, so I'll read it. The influence of added mass seems very small. Do you think it should be larger?
We are not sure. We are now wondering whether our choice of the simulation condition is right or not. And we think we should choose more, how to say, dynamic situation to be compared, because in this situation the motion of ice is more or less how to say small or moderate. So we may well choose more dynamic situation of ice motion. So this is our future plan to conduct how to say more violent situation or something like that. Is that answer his question? About is that okay?
I guess so. Like it wasn't my question, so I hope so. And if not, I encourage the audience to send questions through the organizers, and we'll make sure we distribute them to the authors. So thank you very much for your presentation. And I'll introduce the last speaker of the session. If you could please the presentation and sharing while I'm presenting the fifth presenter, Zongyu Jiang. He'll be presenting the paper Scale Model Ridges and Interaction with Narrow Structures, Part 4, Global Loads and Failure Mechanism. So the floor is yours, and you can start the presentation or upload the presentation and start. Zong, we cannot hear you. There is probably a problem with the audio. You don't seem muted, but there might be a problem. No. We can, like you can try to maybe check your audio to ensure your speakers and everything is connected. And we are not in such a rush because your presentation is the last one. So even if we run a few minutes late, it's not such a big problem.
Okay, so
it works. It works.
Now?
Thank you. Yeah, it works. So if you could start.
Okay.
Perfect.
Thank you very much.
Thank you.
Mm-hmm. My name is Jiang Dongyu, and I'm one PhD student from Aalto University, Finland. And this presentation focuses on the global ice loads on narrow structures and the failure mechanisms of the ice ridge. And this is the fourth publication of the experiment studying the interaction between the narrow structures and the ice ridges. And this presentation has 4 parts, and the first part is motivation. And for the if we want to keep the safety of the structure, we need to know the ice load well. And if we want to know the ice load better, we need to know the failure process of the ice. And so far, we know much more knowledge about the failure process of level ice than that of the ridge. So the one main purpose of this experiment is to observe and analyze the failure process of ridge. And next, I will brief the experiment setup. And this experiment campaign has 4 main stages. And the first one is ice ridge production, and the second is model structure design and build. The third one is to design and test metrics to analyze some influence of the different factors. And the last step is to execute the test. And the ice ridge was produced by 3 steps. The first one was to generate the level ice by spraying the ethanol solution on the water surface. When the level ice was finished, the central part of the level ice was broken into ice blocks, and these ice blocks were pushed together to build a ridge. And if the test was conducted before the consolidating of the ridge, and the test was called non-consolidated test. And if the tests were conducted after the consolidating procedure, they are called consolidated tests. And the left figure showed showed some example of the cross section of the keel. And here we can see that the shape of the keel keel's cross section is similar to the natural ridge, and the maximum keel depth was around 0.4 meters, which was about 10 times of the thickness of the level ice. And the model structure mainly had 2 parts. The first part is the vertical cylinder, and the second part is a cone with a sloping angle of 75 degrees. And when the vertical cylinder penetrated the free surface, and the test is called the vertical structure test. And if the cone part penetrated the free surface, and the tests are called the slope structure test. And one 3-dimensional load cell was installed in the model to measure the global ice load. And in order to observe the failure process of the keel and the process of the ridge, and 6 cameras were installed around the model structure. And 2 of them are above the water, and 4 of them were installed underwater. And the left picture shows the frame for installation of the underwater cameras, and this frame was horizontally installed at the bottom of the structure. And this table shows the test metrics. Here we 3 ice sheets were used for the 8 tests. And all these 3 ice sheets had the same thickness, and that was 4 centimeters. And for different tests, the flexural strength of the level ice was different. This flexural strength can be changed by using different procedures by rising or lowering the air temperature. And next, I will present some results and main findings of our experiment. And first of all, I will show one picture about the rubble accumulation in front of the structure. And here we can see that the lateral projection is a kind of triangle, and it's the area of the projection is proportional to the volume of the rubble accumulation. So we can use one formula to calculate the area. That is, the area is equal to the half product of depth and horizontal extension. And this animation shows how the structure broke the keel of the ridge. And the yellow straight line represents the most forward point of the horizontal extension. And the further observation is that there is no ice block was broken by the structure, and the structure only broke the freeze bond in between ice blocks. And then, according to our analysis, we think that is due to the lower strength of the freeze bond in the keel. And when the structure get close to the ice blocks, and the compressive force became larger and larger. So at a specific point, the freeze bond was broken, and that's why the yellow line stay at one position for a short time and jumped to a new position, and which can be reflected by the horizontal extension curve in the right figure. There is a zigzag shape at the first part of the curve, and at the point of the summit, all the freeze bond were broken in front of the structure. So there is no the structure did not break no more no more freeze bond in between the ice blocks. So there is no zigzag shape in the last part of the curve. And this figure just shows one example of the original history curve of the total ice load. And we can see that there is a lot of fluctuation in the original history curve. So it is hard to compare the result of ice load between different tests. So we employed two envelopes to represent this original history curve. We use the upper envelope to represent the total ice load, and we use the lower envelope to represent the rubber load. And so the difference between these two envelopes can be considered the consolidated layer load here. And these two figures show the rubber loads and the area of lateral projection respectively. And here we can see that the rubber area is proportional to the rubber loads, and all the summits of the curves located at the 3-meter penetration distance. And this figure just shows some peak values of the ice load from different tests. And the first observation is that the rubber loads have small fluctuation between tests. And so we can consider that the rubber loads can it was not very influenced by some parameters very much. For example, the flexural strength or the structural type. And on the other hand, the consolidated layer load can be influenced by the structure type very strongly. And here, for example, in the red box, and the consolidated layer loads load and is much smaller than the consolidated load from the yes, and for the test at test 10 we get a much larger consolidated lower than the test 9, and that is because at test 9 the structure type is the slope, and the slope structure can break the consolidated layer by bending, and of course the load was reduced apparently. And with all the analyze and observation, we can get 3 conclusions. The first conclusion is that this experiment can uncover the failure process of the ridge, and we think it is important and helpful for us to understand the failing mechanisms of the queue. And the second conclusion is that the horizontal extension of the rubble had a pattern of shrinkage and expansion, and this is because of the failure of the freeze bond. So this zigzag pattern vanished when the extension reached the far edge of the ridge, and that's because all freeze bonds were broken in front of the structure. And the third conclusion is that the rubble load was proportional to the volume of the rubble accumulation, and this matches the previous discovery. At last, we want to show our gratefulness to the HydroLab Plus program, and we also want to show our gratefulness to the crew in Aldo S Tank for their valuable help and support. That's all we want to present and share. Thank you very much for your attention.
Thank you very much for your presentation, and I'll check whether YouTube, are there any questions on YouTube or anyone in the Zoom room? Do you have any questions? Maybe with slight delays receiving the questions, I'll ask one question as usually. What are your plans like for the next study or for the next work? As your colleague Funk, he started using the artificial intelligence. Is this something you plan to use, or is there anything else you plan to do after these results?
When we get the results, we can make some, numerical simulation. If we can get some results from the numerical simulation, we can compare the results from 2 kinds of methods. The first one is that. The second is that we can build some formula, some analytical formula to calculate the rubble load from the queue of the ridge. That will be the potential work in the future.
Okay, thank you very much. So one more call for questions, and I don't see any. So that leads me to conclude the session. I thank you all the presenters for preparing papers, presentations, and sharing results here with us. I remind the audience, if you do have any additional questions, please contact the authors through the conference organizers, and I'll let you enjoy the break, 20-minute break before the next session starts. Thank you very much.
Thank you too.
Hello, Jukka.
Oh.
I guess we have an assistant.
I don't know. Do you see my slide?
Okay.
Do you see my slide?
Oh, yes, I see your slide.
Yes,
I beg your pardon. Yes, yes.
Yeah, because I just tested that this sharing works, and it does.
Okay, yes, it's fine. Well, hello, Jukka. Good to see you again.
I'm fine. Yes, and you?
Fine. I guess I better turn my camera on just to show you that I really am here. Okay. Yes, we're enjoying summer. We've had, as you remember, Ottawa can have some very hot days and some not so hot. So we've had some hot, but we're now into a bit more moderate summer weather. And you, I guess you're getting ready shortly. You'll be departing to your summer cottage.
Exactly. Yeah. Summer is coming.
And I think you're pretty well able to live off the grid there, I believe, as you describe it.
Yes. Absolutely.
So other than the sun shining occasionally. And
yeah, it's powerful enough system, so I don't need so much power. Oh, sun, yeah.
Yeah, I guess I was confused. Somehow I thought it was 8 hours time difference between Ottawa and Moscow. But anyway, it seems to be 7. So that's every hour is good.
Every hour is good.
Less is good.
There's no daylight saving time in Russia.
Ah, that explains it.
So winter, it's 8 hours in winter.
Okay. Yes. Okay. That explains everything. We have, you probably don't remember, but Saskatchewan, the one province in Canada, doesn't go on daylight saving time. They stay in sort of standard time year round. So they don't change their clocks, but you have to sort of always make an adjustment if you're trying to contact somebody there as a result. So anyway, right. This is good news. The difference is not as great. I was really fearful because I think Ivana gave an opening address and it was going to be thinking 8 hours. That would have been 4 a.m. in the morning for the conference. And I was thinking, I know she gets up early, but not that early.
Yeah.
So I see. I guess our assistant is there if we need him, but otherwise not. Actually, what I am going to try to do is open up the YouTube channel so I can monitor any questions that come in.
You can do that, but you should be careful because there's a delay, and you need to put the sound off from the YouTube channel, because then otherwise it gets really confusing. I've done it, so I know.
Okay, I'll make sure I turn off the sound on that, and I'll make sure I still have sound here.
Yes.
Yes, and the delay is supposed to be about 40 seconds.
40 seconds, okay.
I'm just going down to open up the YouTube room, and I'll make sure I get the sound turned off. And so it's not only 40 seconds in terms of time, but I guess it would be 40 seconds in terms of somebody typing a question. It will there'll be delay in the yeah, okay. So I've turned off the sound in the YouTube, and I'll come back to Zoom and get full screen, so we have full benefit. Sound, and I'll come back to Zoom and get full screen, so we have full for benefit. Okay, I guess, Yuka, are you doing the presentation?
No, I think, Bob, you have voice on the YouTube. Oh, there's sound now.
Beg your pardon?
Is the sound okay now?
Yes.
Okay, good.
Okay. I see.
Hello, Marnix.
So there's, I guess, I have 3 of the speakers here already. Just Wan Zhang. The second paper, I don't. Marnix, good morning or good afternoon to you.
Good afternoon. Good evening, maybe for you, I think, right? Yeah.
And Polina is there too. Good, good. I'll ask, maybe at this moment, I'll ask you to say hello to Nina. I don't know whether Nina is going to be joining the conference or not. And also Dr. Professor Vladimir Likomanov. I remember meeting him about maybe 25 years ago, 20-some years ago. Visited you at ARI, or visited his office at ARI.
Okay, I will say hello from you.
Thank you very much. He was a very gracious host. It was in the winter time, I think it was maybe January or February, and everything seemed to be so cold. But when I finally, got into ARI and then got to his office, it was it was very, very comfortable, and he was a very, very welcoming host. I guess in terms of keeping on time, we should consider starting. I see it's 20 minutes after the hour. The first presentation is on comparison of full-scale and discrete element modeling simulation data on ship-hull ice loads. And it's a contribution from Aalto University and will be presented by Yuka Tukuri. So please go ahead, Yuka.
Thank you. Thank you. Thank you, Bob, and hello, everybody. Good afternoon or good morning, wherever you are. Today, gonna talk about our joint work with Arttu Polojärvi, Hanyan Kong, and myself on comparison of discrete element results and full-scale data concerning ice loads on ships in ice flow fields. And ice load term here refers to local ice loads. So load on a small patch of area, not like a large scale integrated resistance, but really local ice loads. And we think this is an important issue. With global warming, we will see more and more broken ice fields, so kind of marginal ice zones are becoming more and more common. There's less solid level ice, continuous level ice than earlier, and that's why we need to understand the ice loads in these flow fields. DEMs, discrete element methods, have been used to simulate this kind of flow fields, but very little on the local ice loads. The earlier studies have focused on resistance, but here we now focus on the local ice loads. This is a first presentation of this kind of work by us. So this is kind of ongoing work, and more is to follow. The full-scale measurements that we use here as a comparison are our measurements from Agulhas, shown here, South African research and supply vessel going every Christmas time from Cape Town to Antarctica and then back. And we are measuring ice loads on 3 locations on the hull, 2 locations in the bow and 1 at the aft. And the size of the panel we are here concerned is 0.47 square meters. That's the red one in the front. So waterline width of that panel is 0.4 meters, and then it's 1.175 meters high. The Aalto University has a lot of, the group by Pentti Kujala has collected a lot of data on Agulhas ice loads, but here we concentrate on certain cases on ice flow fields, marginal ice zone style situations. About the simulation part, it has conducted by our in-house 3D discrete element method by the Aalto University Ice Mechanics group. And in this simulation, the version of the code is that the ice blocks are rigid. In this preliminary stage, the ice blocks are not allowed to fail. And I will soon go to some details of the simulations, but the length of the simulation domain is 2 kilometers. Width is 0.5 kilometer. So it depending on the size of the flows and the concentration, we had about 3,000 to 23,000 ice flows in the simulation. And here is some data of the simulations. The flow shape was varied. We report here in this preliminary work of only the data from rectangular flows, but other shapes have also been studied. The ship motion was slow, 1 meter per second. So velocity effects were not studied. We modeled flow buoyancy and ice flow drag, but not kind of serious hydrodynamics. And it's then also said here that in the simulations we were like dealing with the simplified geometry of the Agulhas 2, not exact, but the same dimensions and same angles, but it is not an exact model, but it is a simplified geometry. There you can see, so the effective modulus for the flows was 1 gigapascal, the friction coefficient was 0.5, plastic limit 1 megapascal, which means that with the ice-ice contact or ship-ice contacts occurring, the pressure can go as high as 1 MPa, and as the panel size was, as shown here, so panel size was 0.47 square meters, it means, and 1 megapascal. So that in fact then gives upper limit to the load that we can obtain from the simulations. Here shows the cases that we report here. 2 ice thicknesses, 1 meter and 0.5 meter. Concentration varied from 50% to 80%. The size of the flows, there was like a range of flows from 5 to 15 meters, 10 to 30 meters. And then the number of flows is also shown there on the right. And then visually you can see then how they different, what they look like, a 50% coverage and the 80% coverage. 80% is a high high concentration. And a 3D simulation, this is what it looks like. So there's flows, ice flows that are floating, and then the redshift goes through it. I have a simulation here, not sure how it works. At least it goes quite fast. I hope you can see it. It works on my computer, and that's how it may look like a bullet going through something, but it is a agulhas in an ice flow field. And then here is what we observe. Then the load, the maximum is this 470 kilonewtons. That just comes out from the way we set up the system. And then you see here a 2 kilometer length of the simulated time, and also full-scale data. The full-scale data, the full-scale cases we have, they have a length, minimum length of 2 kilometers and then up to 4 kilometers. And this shows now ice load hits in that panel in the front of the bow. So it's mostly zeros, and then now and then you can see that one ice flow hits that location, and then we see these kind of peaks, and the black ones are the measured peaks, and then the red ones are then from our simulation. So they look similar, and also kind of the load levels are very, very similar. Here is another kind of set of results showing, maybe a little bit surprisingly, at least to me, that the ice thickness appears not to have a strong effect on the mean load. Some peaks, of course, as the type of ice loading is that we have high peaks, those can be seen. But if you look at the kind of the range of values and where the mean is, so there's very, very, if any, there isn't much effect of the ice thickness, and that is both on the simulated loads and also for the full scale. No clear thickness dependence. Table, as is also in the paper, then showing the full scale events, 10 of those altogether, and then what was measured, kind of the average load, and then the maximum load, and then also the simulation side there, the average loads and the maximum loads, and then the 90% quantile also is shown there. So this is kind of the data we have from these simulations that which gives us confidence that this method works. So we have simulated ice loads, local ice loads, and then compared to full-scale data to kind of verify our simulations in a way, and then this gives us the opportunity then to go forward. Compares well with full-scale data. Simulated loads are somewhat larger, but only somewhat larger. And then what we will do next is to concentrate on the flow field properties, ice flow shape, the size of the ice flows, thickness of the ice flows, and what kind of things we can then figure out. What we can study then with this tool we have developed. This work was funded by Deutsche Register Foundation, which we acknowledge with gratitude, and then our colleagues, Dr. Fang Li and soon Dr. Lianlian Lu, helped us to kind of locate the full-scale data used for the comparison with the simulation. Thank you. That's all I had.
Thank you very much, Jukka. Well, first of all, I'll ask: is there anybody on the Zoom call who has a question? I have a couple of questions for you, Jukka. You gave a friction coefficient of 0.5. That apply both to the primarily to the ice, or does it also apply to the ice ship?
Primarily to the. Now I don't remember. I must be honest. I don't remember. But at least to ice. Yes. Yeah.
Oh, okay. I guess just the other thing that I observed from the simulation run, again, maybe it was the bullet-like trajectory of the ship, but it seemed as if the flows are really being sort of scattered to the side. And I don't know if you can go back and run that again, but I guess in my limited experience in broken ice fields, I haven't sort of seen such a wide weight being left behind the vessel as it is here, and it seems to be almost sort of a continuing wedge shape behind it.
Okay.
Just an observation.
Yeah,
thought about that.
Yeah, I'm happy to hear that kind of observations. Yes. Okay. So you kind of think that they are kind of too, they move too much in a sense.
A little bit too energetic.
Yeah.
I'm just going to switch to the Zoom room to see if there are any questions there. I don't see anything. I hope people who are, I'm not a Zoom room, in the YouTube, I hope people who are monitoring on the YouTube channel, if you have questions, please, I've got it open up to take a look to see if there's anything posted there. But I don't see anything, even allowing, I think, for a 40-second delay. Anyway, I'll come back to my to the Zoom. Yeah, and I guess all your flows are basically rectangular, I think. Is that the
here they are. I mean, in the work we report here, they are rectangular, but I mean, we have been working forward this already, and we also have discs, I mean, circular discs nowadays. So yeah.
Okay, and your material model is, you mentioned it, elastic modulus of 1 gigapascal, and it's a plastic model at 1 MPa. It yields plastically then.
Yeah. So 1 MPa is the highest pressure that can be seen.
The results look remarkably comparable to the full-scale measurements.
Yeah.
Given that both the model and the full scale is rather random.
Yeah.
But okay. Any of the other people on the Zoom call, Paulina or?
Yes, I have a question.
Do you have a question? Go ahead.
Jukka, thank you for the presentation. It's very interesting to see your work. I was wondering, I see quite some rafting of ice flows. Do you have any specific rafting model, or can you say something about that?
No rafting model. They raft if they raft. I mean, then it's the point. Then there's friction, but then there's ice friction. Yeah. Yeah. So it's not. Yeah, no rafting model. It's just contact model. if that's what, if that is what you mean. Yeah.
Yes, indeed. That's what I mean. Would you say if the, let's say, if the simulation would be completely, if the ship would have completely vertical sides, let's say? I'm not sure if that's the case here.
No, it's not. The sides are vertical. Yeah, the bow is not, but the sides are rather vertical.
Okay, yeah. If the bow would be completely vertical, would you still get rafting, or is that something that's introduced by the sloping angle of the bow?
Good question. I don't know. I would assume yes, but that's based on my own. That's based on other simulations and lab work I have done. That does not affect. Of course, it helps, but it's yeah. Eventually, if everything was totally vertical, then you would kind of push the ice more onto the sides. But then when there's kind of contact and a force change start to form at some stage, and then they will buckle and then they start rafting. I would guess, but no, we did not test it here. But in earlier work, I mean, in the 1990s when I did this also. So then we got rafting with just compressing and flow feed.
Yeah, thank you for your comments. I think I agree with you basically on that. But still, I think it's especially in full scale. To my knowledge, there's not really good understanding of when rafting would occur in such a flow shape, and that applies to my presentation. That will come later. But that's.
I guess would the hull angle cause some tipping of some of the floors?
Yeah, in the bow, exactly. That's what I guess. That's what the discussion was about. Yeah. That it makes it. I think Marnix thinks that it makes a difference. It may well be. Yes, I don't know.
Yeah.
Okay. I'll thank you very much for your presentation, Jukka, and the paper from you and your colleagues. I'll ask whether the second speaker who is on the program, Yan Zhang from Harbin Engineering University, is he present, or the room assistant? Have you heard any information as to whether that presentation was submitted to you, or have you heard anything from the authors?
No, actually, I don't have any information.
Okay. I guess with the the concurrence of Paulina and Marnix, would you agree that we should proceed rather than sitting for 20 minutes? I don't know how many people switch back and forth between sessions. Probably not that many. So I propose I'll take it upon myself to proceed and ask Paulina if she could get her presentation set up. This is on ice load monitoring systems for an ice-resistant self-propelled drifting platform, North Pole. She's presenting on behalf of herself and her co-authors from the Arctic and Antarctic Research Institutes. I think it's still called the Laboratory of Ship Performance and Ice. I welcome you, Paulina. You have the floor and the microphone.
Hello, everybody. I'm here.
Welcome, and you're on.
So, do you see my presentation?
Yes, looks good.
Yes. Okay, then I'm ready. Today I will talk about the development of ice load monitoring system for an ice-resistant self-propelled drifting platform North Pole. The platform was created to provide more comfortable and safe working conditions for polar explorers. The platform will replace the classical drifting stations North Pole, which were located directly on the drifting ice. The platform is intended for performing functions of a research station under the conditions of drift, together with the surrounded ice massive up to 2 years. The main operation mode of the platform is a long-term drift in high latitudes. It means that platform will interact with multi-year back ice. This is why the hull strength at the bottom and sides corresponds to ice class Arc 8 of Russian register. It is almost the highest ice class for ice navigation vessels. But at the same time, the propulsion of the platform is not very powerful. The platform has one port drive and hydraulic azimuth thruster in the bow. This is due to the fact that the independent movement of the platform is assumed only in relatively light ice conditions. On the 18th of December in 2020, the platform was launched at Admiralty Shipyards in St. Petersburg, and the first scientific voyage of the platform is planned in 2022. The platform is a unique facility which required developing of a non-standard ice load monitoring system. In addition to provide safe operation of the platform, the system has to perform scientific functions. Two main scenarios of ice impact on the whole platform were selected for monitoring. Impact loads on the bow and stern at motion under the ice conditions during transit and moving to an ice floor, and loads from compression ice on the mid-body part of the platform during the drift. Based on the analysis of the ice conditions and the hull strength, it could be noted that ice loads that occur during the platform motion in ice condition is significantly less dangerous than the loads from compression ice. So based on the results, taking into account that the most of time the platform will drift in ice, the ice load monitoring system primarily aimed of monitoring the mid-body part of the platform during ice compressions. To evaluate the influence of ice compressions on the platform hull, model tests in RE ice basin were carried out. Model experiments make it possible to determine distribution of ice piles along the sides of platform and under the bottom. Based on results of model tests, the area of platform pools which should be equipped with sensors for monitoring were determined. The technology of platform operation was testing in spring of 2019 in Transantarctic project. The first stage of project consists the long-term drift of research vessel Akademik Treshnikov in ice on the north of Barents Sea. This allowed us to test the technology of ice monitoring system under the drift conditions. As measuring tools, we used factory ice load monitoring system of Akademik Treshnikov, and additionally installed strain gauges at the section of the hull. Based on the results of measurements, a number of peculiarities in the operation of ice load monitoring system during the drift was determined, and we found some new ideas for design the monitoring system for the platform. Now some words about the architecture of ice load monitoring system for the platform. The system consists of two measuring parts. One is on board the platform and another is on ice floe. The main onboard part measuring system is house stress monitoring subsystem. In this system, we used a set of fiber optic sensors, triaxial and uniaxial strain sensors for measuring deformations, and temperature sensors. They are necessary to distinguish between structural deformation caused by external forces and thermal deformations. Also, the onboard system includes 4 subsystems, which are necessary for additional information required for analysis of ice loads. The subsystems provide data about geographical coordinates of platform, speed, and also whole motion parameters as a solid body, meteorological parameters, and proportional complex parameters. Outside the platform, the membrane pressure sensors are installed on the ice as a subsystem of stress strain state parameters of ice cover near the platform floor. The subsystem will be used only during the drift of the platform. Data from all subsystems is recorded as a united database with a frequency of 100 Hz. The storage capacity will make it possible to store all information during 1 year of continuous recording. The system control post will be located in ice load monitoring laboratory, and also the system monitor will be installed on the navigation bridge. This slide shows the full stress monitoring subsystem sensors locations. Most of sensors located on the midship part of the hull, and most of them located on the starboard. Some of them are located on the port side symmetrically, and some of them on the bottom. The sensors located along the entire length and side height, and also sensors located in form of 2 lines because of the significant change of platform draft during the drift. So the lines correspond to maximum and minimum drafts. The location of sensors and structural elements on which they are installed were determined based on the results of finite element analysis. This slide shows the installation of pressure sensors. At the initial stage of the platform operation, we will use 6 simple membrane pressure sensors with diameter of about 20 centimeters filled with hydraulic liquid. These sensors are intended for freezing into ice a distance from the platform is about not less than 100 meters. It is supposed that the sensors will be located in the ice in 2 show perpendicular direction at different horizons across the ice thickness. Additionally, also ice thickness measurements and physical mechanical properties of ice will be carried out at the same point every 10 days to obtain clear picture of ice thickness and ice properties change. The next two slides is about software of ice load monitoring systems. The software package was designed by NTI company, and the technical requirements were developed by Department of Ship Performance in ICE of RE. Now we have demo version of software, and it is being tested. Now we see on this slide, you can see the main screen of the program with location of sensors, and the value for each sensor is given in the tabular form. Also, here you can see the parameters for all subsystems. Software also allows to display in real time all current data from all subsystems, allow to display any data of the system from the database. And also software automatically mark high load events and display recorded events in the form of histogram with depiction of the number of events for chosen interval. The alarm screen is intended for navigator and provide information about hull stress levels during operation in ice. The main view of the platform is divided on sectors, which are highlighted in different colors depending on ice level of ice load. We expect that the ice load monitoring system will perform following functions. Operational function is provision of safe operation of the platform under the ice condition. And the main function is scientific function. The list of scientific capabilities you can see on the slide, but perhaps this list will be expanded when we start using monitoring system in field conditions. But at the moment, in our opinion, the most important opportunity is joint study, joint measurements of stresses in ice cover and in the full of the platform. And also, important task is verification of existing methods of calculation of stress strain state of the ice loads on the hull and methods of numerical modeling of ice compressions. It is quite possible that scientific programs implemented during the ice drift of the platform will be international. So maybe some of you will have some ideas about how to use the monitoring system, and we are open for cooperation. And in conclusion, I would like to say that the issue of naming the platform after the former director of the RE, Ivan Frolov, is currently being considered because in the last years of his life, he did a lot of implement this project. Thank you for your attention.
Thank you very much, Paulina. A very nice and interesting presentation. I think it's a dream project that many people think about. Very few people or organizations have a chance to realize something like this. There were actually 29 people watching on the YouTube channel also. So I first of all see any immediate questions from the people who are on the Zoom meeting. Maybe just on that, I was going to just ask just a more or less a technical question. The on-ice measurements, that will be wireless connections to the ship. So depending upon if the ice flow happens to move a bit further away from the ship, you're still receiving the information from those instruments, or are they? Or is all that logging done actually right in situ on the ice flow?
Maybe I don't understand clearly, but we will not use, no, at the first stages, we will not use the wireless connection.
Oh, okay, thank you.
Maybe later.
I'll just check the Zoom. Okay. I see one answer from Nina already. I'll just wait a minute on this on the YouTube channel in case there are any other questions that people. It takes a minute to type the question in. The second sort of loading scenario which you described in the presentation, that sort of relating to the ship in pressured ice. I guess one aspect of that, of course, is the measurements that are being made by the instrumentation on the ship, and I presume there would be general meteorological conditions being monitored at the same time, so that the external meteorological environment could be added into the actual measurement information.
Can you repeat, please?
Okay, I'm just looking at the okay, I don't see any more questions there. Let's come back to the Zoom. If there are no other questions, again, thank you very much for a nice presentation, a fascinating paper. This is a project, as I say, that I think many organizations in many countries dream of maybe doing something like this. And again, you're to be congratulated in the success of getting this project underway, and good success to you when you deploy it, I think, in 2022.
Yeah, thank you very much. We are ready for cooperation.
Okay, again, thank you very much. Okay, okay, moving on then, I'd like to ask Marnix to bring up his presentation. This is from the the full title here: Numerical Modeling of Ice Pressure Effects on Ice Resistance During Ship Station Keeping in Broken Ice. So maybe in a few years you will have some data from the North Pole Station to compare with your numerical model. So again, Marnix, please go ahead with your presentation.
Thank you for the introduction. Yes, yes, I will present a small study we did on numerical modeling of ice pressure effects on the ice resistance during station keeping in broken ice. I will present on behalf of my co-authors Ryan Lubat and Sveinung Løseth. This study was motivated by an earlier study that we have done to assist in the ship selection for a scientific coring campaign, ARC-OP, which stands for Arctic Ocean Paleoceanography. So for this ARC-OP project, we performed a series of numerical simulations to assess the station keeping capability of several ships in managed ice conditions. And this figure on this slide shows the initial condition of one of the simulations that we have performed for the ARC-OP project. So this presentation does not directly contain the results from the ARC-OP study, but we made some observations in the simulations done for ARC-OP that motivated the study that's presented here in this thesis. And now in this work, we go a bit beyond the design conditions for ARC-OP. So during ARC-OP, we assessed the influence of some factors on the ice resistance of ships, among other things, the ice concentration, flow size distribution, and the ship geometry. And we performed simulations with the same broken ice, which represented managed ice, but with different boundary conditions. And we found that the assumption on the boundary conditions had quite a significant effect on the ice loads and ice resistance of the simulated ships. And the effect of boundary conditions was also related to the hull shape of the ships. So for some ships, the effect of boundary conditions was stronger than for other ships. And so this led to some further questions, and that was the reason for the current study. So one of the questions that was raised was how are the effects of boundary conditions and ice pressure related to the ship resistance for different hull shapes? And a second question is if the effect of certain boundary conditions and the confinement that these conditions may cause, if that can be seen as equivalent to an ice field with an external ice pressure that is imposed by wind and current. So the hypothesis there is that by having a confined domain and a propagating ship, the propagation of the ship would also cause a local pressure, in-plane pressure in the ice cover. So to study these questions further, we performed a series of numerical simulations. We performed 3 simulations with the same broken ice field representing managed ice, but with different far field or boundary conditions. This is shown in the upper left corner. We performed 6 simulations with the same broken ice, but with different ice pressure conditions ranging from 0 to 6 kilonewton per meter. And all these simulations we performed for 2 different ships with different hull shapes shown on the lower left corner. And in the coming slides, I will go into a bit more detail on the specific conditions for the simulations. So in the end, the condition that we are simulating, this is an artist's impression of the condition we are simulating. So it represents a drill ship that's station keeping, so staying on location in ice that is drifting under the influence of wind or current. And the ice is managed before it reaches the drill ship, so leading to quite limited flow sizes. And around this region of managed ice, there is unmanaged ice represented by much larger flows. The ice management operation itself is not modeled in this study. So we just take the managed ice as an input, and then we make different assumptions on the properties of the, let's say, the boundary conditions or the unmanaged ice around the region where the ice is managed. So some motivation for the different, let's say, far field ice properties we chose. When you look at satellite pictures of broken ice, this slide shows 2 examples. There's quite a difference in the conditions that you can see. Even for similar flow sizes and ice concentrations, there are also other differences that can be seen. For instance, here in the left picture, we see an ice field that appears to be recently formed. I conclude that from the still angular forms of the ice shapes. And that's probably under a divergent wind or current condition. So the ice flows apart from each other, let's say. And this can be seen from the long open leads between the ice flows. In the right figure, we see an ice field with much more rounded flows, which in my view indicates that it's been broken up somewhat longer ago, and there has been more interaction between the different ice flows, which rounds off the corners. And also we see that the flows form more or less continuous contact network. So these open leads that we see in the left figure are not visible here. And because of this continuous contact network, such a broken ice field can possibly contain in-plane ice pressure. So these two different far field broken ice conditions we included in the numerical simulation, as shown on this slide. So the left figure represents the condition with long open continuous leads between the ice flows. And the middle figure represents the condition where the ice flows form a continuous force network. And this force network prevents the movement of the flows to a large extent. The near field conditions, so the ice around the ship, is the same in both simulations, as is shown on the right. Finally, the third condition, in the third condition, the far field ice, the unmanaged ice, is represented by rigid confining walls. And to account for the fact that the far field ice is 90% concentration and not 100% concentration, we only cover 90% of the boundary with the confining wall. So there are some gaps there. However, these gaps, we see from the numerical simulations that not much ice clears from these gaps. So it's effectively almost fully confined. In addition to these simulations with confinement, so in these confined simulations, there's no initial in-plane pressure in the ice. We simulated 6 conditions where we imposed an external pressure, P, as shown on this slide, that can be seen as being introduced by the wind or the current conditions. So this simulation domain is confined by a fixed boundary, so a static boundary on the lower side, and by dynamic rectangular beams on the left, right, and top sides. And these beams have a mass equivalent to an ice field extending 11 kilometers in each direction in order to represent the inertia of the far field ice. And the pressure P then varies from 0 to 6 kilonewton, and it's constant in each individual simulation, so that 6 simulations have been performed with this domain for each ship. The simulated ships are the Dina Polaris and the Vidar Viking. These are existing ships that both have drilling capability. Dina Polaris is capable of going in ice, but it is also made for operating in open water. It has a bulbous bow, and it has a relatively steep normal angle at the bow. So the bow is close to vertical, let's say. The Vidar Viking, on the other hand, really has an ice-breaking bow with quite a low normal angle of 38 degrees. And the overall dimensions of both ships are quite similar. So some more info on the environmental properties in all the simulations. Generally, the properties shown here were equal in all the simulations performed. So the ice concentration, both in the managed ice section as well as in the far field where that applies, was 90%. The interaction velocity between the ship and the ice was 1 knot, or approximately 0.5 meters per second. And the table on the right shows the flow size distribution of the managed ice. Diameters of flows ranging from 1.5 to 25 meters, and thicknesses ranging from 1 to 3.5 meters. And the majority of the ice area is represented by the smaller ice flows. The numerical simulations were performed with the SAMS simulator for Arctic marine structures. This is a discrete element simulator developed at NTNU for the assessment of ice loads on ships or structures. The contact forces between ice flows and between the ice and the ship are solved using an implicit discrete element model, or null-smooth model, it can also be called. It considers ice crushing and splitting and bending failure, and hydrostatic forces and drag resistance is considered both on the ice as well as on the ship. Okay, so now we go to the results of the simulations. This figure on the left shows the ice resistance, so the mean ice load in the search direction on both ships for the 3 conditions with different far fields. And we see that for far field 1, where there's a long open lease between the ice flows, that this results in the lowest resistance, and this is caused by the fact that these ice flows, they only have some inertial resistance in the far field, and otherwise they're free to move away. And this also happens due to the ship propagating, and that leads to an effective lower concentration in the region close to the ship. In far field 2, because the far field flows form a continuous force network, this clearing of the flows is inhibited to a large extent, leading to a somewhat higher load. And in the case with rigid confining walls, then the domain is really confined, and this leads to the highest resistance. We also see that the resistance development is different for the 2 ships. So Dina Polaris has a slightly lower resistance for far field 1, but has the highest ice resistance for the domain with rigid confinement. So it appears that the effect of the far field of confinement or confinement conditions is larger for the Dina Polaris hull shape. These 2 figures show the results of the simulations where an initial in-plane ice pressure is applied. And the left figure shows the ice resistance of both ships as a function of the pressure P. And we see there's really a very strong influence of the ice pressure on the ship resistance. For the Dina Polaris, it's almost a factor 10, in fact, increase in ice resistance, going from 0 to 6 kilonewton per meter ice pressure. And again, here we see that the ice pressure has a stronger effect on the ice resistance of the Dina Polaris than on the ice resistance of the Vidar Viking. We also distinguished between the resistance component caused by frictional forces on the hulls and the complete total resistance. And that shows that the frictional resistance increases as a function of ice pressure, but it's never the governing resistance component. It's always the clearing of ice which gives the governing resistance, and not the ice friction on the size of the ship. So this is shown in the right figure, where the frictional resistance as a proportion of the total resistance is plotted for both ships, and the frictional resistance never exceeds 34% of the total resistance. So that's the numerical results, let's say. We can understand the difference between the 2 ships primarily by looking at the visualizations of the simulation results. So this shows the ice clearing behavior of Dina Polaris for a condition with no ice pressure on the left, and a condition with an ice pressure of 6 kilonewton per meter on the right. When there is no in-plane ice pressure, ice almost exclusively displaces in plane. So there's almost no vertical displacement of the ice flows, and some splitting failure is observed for the larger flows. When the ice pressure is 6 kilonewton per meter, on the other hand, there is both in and out of plane displacement of the ice flows. So the ice flows are also displaced vertically. Ice flow rafting is observed, and there is more splitting failure occurring. And what you can also see is that the open channel behind the ship is shorter when there is ice pressure than when there is no ice pressure. For the Vidar Viking, when there is no ice pressure, there is both in and out of plane displacement of ice flows caused by the lower normal angle at the bow. Some bending failure occurs for the larger ice flows, but not so much. And when the ice pressure is 6 kilonewton per meter, there's almost no more in-plane displacement of the ice flows. And the ice flows are primarily displaced out of plane, so vertically. And also more bending failure is observed. So that's the numerical results. As any numerical model, our model is, of course, a simplification of reality. And therefore, we thought about what simplifications of the model might influence the results that I discussed. And I listed 3 main potentially influencing factors on this slide. First of all, the simulations only consider planar ice features with completely vertical sides. And this might lead to less rafting or less out-of-plane displacement than might occur in reality. Also, friction between ice and between ice and the structure is assumed to follow the Coulomb friction law. And finally, the numerical representation of ice rafting. Ice rafting can occur, but whether it occurs at the same pressure as in reality, that's an unanswered question, I think. So based on numerical results and our assessment of the validity, I think the following observations and conclusions can be drawn. So regarding the effect of boundary conditions and ice pressure in relation to the ship resistance and the ship hull shape, we see that ships with a higher bow normal angle, so more vertical sides, let's say at the bow, have an increased effect of in-plane pressure and also of confinement. And I think this can be explained by the fact that boats with a steep normal angle have to displace the ice more in plane, whereas ships with a lower normal angle can displace the ice out of plane. Regarding the second question, is the effect of confinement in numerical simulations equivalent to external ice pressure imposed for wind and current? Yeah, I think we see the same phenomena occurring independent of whether the pressure is caused by confinement and the ship propagation or by external pressure. But we do see that the confinement is only equivalent to quite mild external pressure below 1 kilonewton per meter. And that when the external pressure increases, then it has a much stronger effect than any confinement condition. Finally, I would like to acknowledge Arctic Marine Solutions for providing the ship hull geometries and the ice conditions that we use in the simulations, and Swisha Govinda for digitizing the ship hull geometries from the line drawings. That was my presentation. Thank you for your attention.
Thank you very much, Marnix. I welcome any questions from, I guess, first of all, any of the people who are on the Zoom call. I did note that there is one question from Cody for you, and it is, what was the motivation for selected ice crushing pressure of 2 MPa?
Yeah, I think this is one of the parameters that anyone needs to make an assumption on, and no one, it's a bit unclear what would be the correct value there, because it's simply a simplification of reality. The 2 MPa is representative for quite local ice crushing, so where there is a relatively small contact area. Yeah, I cannot really say much more about it than that.
Okay, actually, thank you. I had a sort of a question too. You described those 3 conditions. There was sort of the very simplified flow form 1, there was a flow form 2, and then there was a rigid wall condition. And the result, the difference between the results was that, would you say that would be more due to the floor shape or the boundary conditions that you're applying in those 3 conditions?
Yes, so that relates to let's say, these conditions. Yeah, so the flow shapes in the domain around the ship are the same in all the cases. And what I think is the main cause of the difference is that in the let's say in the figure shown here on the left, the flows are not in contact with each other. There's long open leads between the flows, and that allows them to displace. So that they only have some inertial resistance, and otherwise they can displace. While in the middle figure, that's for the same ice concentration, but all the flows form a continuous contact network, and they cannot really displace because of that, and that causes a higher confinement in the near field. So the arrangement of flows rather than the flow shape, I would say, yeah.
Okay, thank you. Any other questions gained from the other people in the Zoom? And I'll check the YouTube one more time. Oh, okay. I don't see anything there. So I think on that basis, I will thank you very much. I thank all three speakers, Jukka, Pauliina, and yourself, Ernix. And I wish you all a good afternoon and a good evening and a good morning for anyone who is actually joining from North America. So again, thank you very much. And we'll see you all certainly the next conference and then maybe the next sessions then too. So again, thank you. And until tomorrow. Bye-bye.
Thank you. Bye.
Thank you.
Bye. Bye.
Bye all.